Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, where big questions are allowed to unfold slowly, and where the universe can be explored at a pace gentle enough to drift beside. Tonight, we're taking on a question that sounds simple at first, but becomes stranger the longer you hold it in your hands. Where are we in the universe exactly? Not in the casual sense. Not just the city, town, or street where you happen to be listening right now. Not only the room around you, or the bed, sofa, train seat, or quiet corner where this voice has found you. I mean truly, precisely, astonishingly, where are we? If someone from a distant civilization asked for directions to Earth, what would we even say? Turn left at the spiral galaxy? Continue past several million stars and look for the modest yellow one with 8 planets and one species currently arguing online? It becomes clear very quickly that cosmic navigation is less straightforward than finding the nearest grocery store. Before we begin, I'd love to ask you something gentle and simple. Where are you listening from tonight? What part of the world holds you at this moment? And what time is it there now in your own little local pocket of Earth's turning surface? If you find this soothing, calming, or pleasantly distracting from the usual busyness of life, I'd be grateful if you gave the video a like, maybe subscribed and returned whenever you'd like another slow journey through science. It helps this quiet corner reach others who might also need a softer ending to the day. Now, settle in, let your shoulders loosen, let the day be done for a while. Because to answer where we are, we'll need to travel without moving, measure distances too large to picture, and gradually widen the circle of home. We often imagine ourselves as still. You are seated, lying down, or resting somewhere stable. The floor feels dependable, the walls appear fixed, the room seems calm and unmoving. Yet even now, without the slightest sensation of motion, you're being carried through space at remarkable speeds. At this moment, Earth is spinning. If you are near the equator, you're moving with the planet's rotation at around 1,670 kilometers per hour. If you're farther north or south, the speed is lower but still substantial. Entire cities, oceans, mountains, forests, and sleeping cats are rotating together in one smooth motion. You do not feel it because everything around you shares the movement. The air, the furniture, the roads, the trees, your tea mug, your socks, all turning together. Motion, when perfectly shared, can feel exactly like stillness, and that is only the first layer. While Earth spins, it also travels around the Sun at roughly 107,000 kilometers per hour. Every second, our planet moves nearly 30 kilometers along its orbit. By the time you finish a long blink, Earth has already gone farther than many people walk in an afternoon. Still, no rushing sensation, no cosmic wind in your hair, no dramatic soundtrack, just the quiet confidence of orbital mechanics doing their work. Yet the Sun itself is moving too. Our star, carrying all the planets with it like a lantern leading a small caravan, orbits the centre of the Milky Way galaxy at around 828,000 kilometers per hour. That means the entire solar system, including Earth and everyone currently searching for their misplaced charger, is sweeping through the galaxy at extraordinary speed. And the galaxy moves as well. So when we ask where we are, we must immediately face an odd truth. We are not standing in one place waiting to be located. We are moving on several levels at once, nested inside motions within motions like a set of spinning wheels mounted on a ship sailing across a river carried by an ocean current. It sounds complicated because it is. Still, humans are fond of addresses. We like labels. We enjoy saying things such as third floor, left door, second house on the street, apartment with suspiciously healthy houseplants. We build maps because they calm us. A map says the world can be known. So let's begin with the smallest useful address. You are on Earth. That may sound obvious, but it is already meaningful. Of all the places known to us, this is the one place confirmed to have oceans, weather, forests, deserts, languages, bread, jazz music, penguins, and people trying to remember why they entered the kitchen. Earth is a rocky planet orbiting one star among many. It is not centered in the universe. It is not physically large on cosmic scales. It does not occupy a privileged location. And yet, for us, it is priceless. Every memory you have ever made happened here. Every story you know began here. Every human voice ever spoken first rose into Earth's air. Your personal coordinates can be narrowed further. You're on one hemisphere, one continent or island, one region, one landscape, one building perhaps, one room, one exact point on a turning sphere. That sphere is tilted by about 23.5 degrees, which is why seasons exist. It has a magnetic field that helps shield life from charged particles from the sun. It has an atmosphere thick enough to breathe, thin enough to let us see the stars, and dramatic enough to produce thunderstorms that seem determined to impress everyone. If Earth was smoother, flatter, or slightly different in many ways, our lives would not look the same. Even the place beneath you right now carries a long geological history. Stone under cities may once have been seabed. Fields may once have been glaciers. Mountains may once have been lower, younger, or entirely absent. Your address is not only spatial, it is historical. The ground beneath modern streets can be ancient beyond imagination. Beneath sidewalks are sediments. Beneath sediments are older layers. Beneath those, deep rock formed under pressures far older than human memory. So if someone asks where you are, one answer could include not only latitude and longitude, but several 100 million years of geological backstory. This is the sort of thing the universe enjoys doing. Nothing is ever just one thing. Now imagine zooming upward. The house becomes a roof shape. The street becomes a line. Your neighborhood becomes a pattern. Rivers curve like threads. Highways glow faintly at night. Borders vanish because the land itself does not recognize them. Clouds drift over oceans, unconcerned with politics. From orbit, many things we treat as enormous become small. Stadiums disappear. Towers become tiny marks. Entire cities become clusters of light. The planet reminds us that scale is a flexible emotion. Astronauts often speak about this change in perspective. Looking down at Earth, they do not see separate nations etched into the soil. They see one world, one atmosphere, one fragile blue edge fading into blackness. That blackness is not empty in the everyday sense. It contains radiation, dust, magnetic fields, wandering particles, sunlight, and the enormous distances that make space feel both quiet and severe. Our moon circles nearby, on average about 384,400 kilometers away. Nearby in cosmic terms can mean a distance requiring days of travel by spacecraft. Space has a habit of redefining words like close. The moon has accompanied Earth for billions of years. It steadies our planet's wobble, influences tides, and has inspired poetry, calendars, myths, and many photographs taken through slightly ambitious phone cameras. If Earth is home, the moon is the neighbour visible from the driveway. Beyond that lie the planets of our solar system. Some rocky, some giant, some ringed, some stormy, some cold enough to make winter seem friendly. They orbit the same sun, each following paths governed by gravity's patient rules. Yet even the full solar system is only our local district. We tend to picture the planets crowded neatly together because textbook diagrams need to fit on a page. In reality, the distances are huge. If Earth were a marble, the scale spacing to outer planets would stretch across fields and roads. Most of space, even in a planetary system, is space. That may be one of the universe's favourite design choices. Leave room between things. Then there is the Sun, our star. It contains more than 99% of the mass of the solar system. Everything else, planets, moons, asteroids, comets, dust, all orbit this bright central engine powered by fusion deep in its core. We owe the Sun nearly everything practical. Light for plants, heat for climate, energy stored in food, weather systems, sunrise moods, sunsets people insist on photographing. Without it, Earth would become a dark, frozen memory. And still, the sun is only one star. At night, many of the points overhead are suns of their own, often much farther and stranger than they appear. Some larger, some smaller, some older, some born with planets, some already dead, though their light is still on the way. This creates another curious fact about where you are. When you look up, you are also looking back. Light takes time to travel. Moonlight is about 1.3 seconds old when it reaches you. Sunlight around 8 minutes. Light from distant stars may be years, centuries or thousands of years old. You never see the universe exactly as it is now. You see it as it was when the light began its trip. So where are you? You are on a moving world, around a moving star, inside a moving galaxy, observing delayed messages from distant places while occupying a present moment that itself is difficult to pin down. Not bad for an ordinary evening. There is comfort in this too. Sometimes daily life shrinks around tasks, worries, inboxes, bills, unfinished conversations, and the mysterious disappearance of one matching sock. The scale becomes narrow. Everything feels immediate. Then astronomy gently opens a window. You remember that your concerns exist on one small but meaningful layer of a much larger reality. The kettle still needs boiling. Emails may still wait tomorrow. But tonight, you're also a conscious being resting on a planet suspended in vastness, aware enough to ask where you are. That is no small thing. Among the many known objects in space, we have not yet found another place where the universe sits up and wonders about itself in quite this way. Perhaps such places exist. Perhaps they are common. Perhaps they are rare. We do not yet know. But here at least the cosmos became self-aware enough to make maps, ask questions, and occasionally eat snacks at inconvenient hours. That means your location is more than coordinates. It is part of a rare phenomenon, awareness happening somewhere. Most days, we don't think very hard about location. We wake up somewhere, move through familiar rooms, cross streets we know, sit in chairs we trust, and let the idea of place remain comfortably unexamined. We say things like, "I'm here," and everyone seems satisfied with that answer. It works beautifully in ordinary life. If someone asks where you are, they probably want a city, a building, perhaps a cafe with decent lighting and questionable pastries. Nobody expects you to reply, "I am currently on the outer crust of a rotating silicate sphere moving through interplanetary space." Though it would certainly make meetings more memorable, yet the more gently we inspect the phrase, "I am here," the stranger it becomes. What does it mean to be somewhere? How does your mind create the feeling of being located in a specific point in the world? Why does one room feel familiar and another feel disorienting? Why can the same place feel comforting one day and unfamiliar the next? And how can we feel lost even while standing exactly where we meant to be? Tonight, before we return to galaxies and stars, we stay close to home for a while. Because to understand where we are in the universe, it helps to understand how we experience being anywhere at all. At this moment, you likely feel positioned. You know roughly where your hands are, where the floor is, where the walls are, and where the nearest source of comfort may be located. Perhaps a pillow, perhaps a blanket, perhaps a snack hidden with admirable secrecy. This sense of orientation feels automatic because it mostly is. Your brain is constantly building a model of where you are. It uses signals from the eyes, inner ears, muscles, joints, skin, and memory. Vision tells you about distance, shape, movement, brightness, and boundaries. Your inner ear detects balance, acceleration, and head position. Muscles and joints report posture and motion. Touch confirms surfaces. Memory adds expectations. Together, these streams become a seamless experience we call being somewhere. You do not consciously calculate the angle of your neck, the tilt of your torso, the pressure under your feet, and the location of the door. Your brain handles the math behind the curtain and presents the polished result, a stable world with you inside it. That stability is impressive, because the raw inputs are messy. Your eyes move rapidly several times each second. Your head shifts, light changes, sounds bounce unpredictably. Your body sways even when standing still. Yet instead of chaos, you experience continuity. The room remains a room. The bed remains where beds traditionally prefer to remain. The ceiling behaves with reassuring consistency. Neuroscience sometimes reveals wonders by describing what we no longer notice. Consider balance. Hidden within the inner ear are tiny fluid-filled structures and sensory cells that detect motion. When you turn your head, lean forward, or roll over in bed, these systems report the change almost instantly. They help keep vision steady and posture coordinated. Without them, simply standing upright can become a challenge. This means your feeling of being somewhere depends partly on microscopic movements of fluid in your skull. A poetic sentence it is not, but a marvellous one all the same. Then there is proprioception, sometimes called the sixth sense. Though humans have named many things the sixth sense with generous enthusiasm, proprioception is your awareness of body position. Close your eyes and touch your nose. Most people can manage this without requiring navigation lights. That ability comes from sensors in muscles and joints telling the brain where each limb is. You feel located not only in the room, but inside your own body. That might sound obvious until it goes wrong. Under fatigue, illness, injury, or neurological disruption, the sense can wobble. People may feel clumsy, off-center, strangely detached, or spatially confused. The normal ease of being embodied is something we appreciate best when it temporarily misbehaves. Now add memory. Walk into a childhood home, an old-school hallway, or a street you haven't visited in years, and place rushes back with surprising force. You may remember smells, sounds, emotions, even the way afternoon light once landed on a wall. A location can unlock entire shelves of memory. The brain stores place richly. Part of this involves the hippocampus, a structure deeply linked with memory and navigation. Within related brain systems are cells that help map space. Some fire when you're in a specific location, others track direction or distance. In a real sense, your brain contains internal mapping tools. You're carrying navigation equipment older than maps and more elegant than most phone apps, though admittedly less useful when searching for whichever drawer currently contains batteries. Researchers discovered place cells in rats, neurons that become active when the animal occupies a certain area. Later, grid cells were identified, firing in repeating patterns that seemed to help measure space. These discoveries suggested the brain builds coordinate systems of its own. Long before satellites, brains were already solving location problems. This matters because the feeling of being somewhere is not merely sensory. It is computational. Your nervous system predicts, updates, corrects, and integrates information continuously. It asks, where am I? Where am I moving? What is nearby? What changed? What matters? Where is the wall I walked into last time? Usually it answers so smoothly that you never notice the questioning. Sometimes, however, the system reveals itself through mistakes. Have you ever woken in the night and briefly not known where you were? Perhaps in a hotel room, a guest room, or after an afternoon nap of suspicious ambition. For a few seconds, the map is missing. The walls are unfamiliar. Orientation has not yet loaded. Then memory clicks into place, and the world returns. Those seconds can feel surprisingly deep. Or consider stepping onto an unmoving escalator. Many people experience a tiny jolt of awkwardness. The brain expected movement and prepared accordingly. When reality differs, coordination stutters. It is a reminder that place is partly prediction. The brain does not passively receive the world, it actively guesses it. That principle appears everywhere. If you enter your dark kitchen at night, you often know where objects are before seeing them. If furniture is moved, your shin may learn before your eyes do. The body trusted an outdated map. This is one reason familiar places feel comfortable. They reduce uncertainty. The brain already knows likely distances, pathways, sounds, and surfaces. Familiarity lowers workload. You can move half asleep to the bathroom with confidence that architecture has remained cooperative. New places demand more attention. A strange apartment, airport terminal, or unfamiliar city requires constant updating. Which door? Which direction? How many stairs? Why does every corridor appear designed by someone opposed to clarity? Novel places can be exciting, but they cost more mental energy. This may explain why travel can feel both invigorating and tiring. The brain is busy mapping. There is also emotional geography. Some places feel safe, others feel tense, some feel lonely despite crowds. Others feel warm because of memories rather than temperature. Human experience stains locations with meaning. A bench can become sacred because of one conversation. A street corner can feel heavy because of one loss. A kitchen can become home because laughter happened there repeatedly. Physical coordinates stay the same while emotional coordinates shift. So where are you exactly? You are in measurable space. Yes, but also in remembered space, expected space, felt space. This is why moving house can feel larger than changing walls. You're rewriting maps in body and mind. The route to light switches changes. Morning sounds change. Windows frame different skies. Even silence sounds different in a new place. Home is partly architecture and partly neural familiarity. Children reveal this beautifully. Very young children often define location relationally rather than abstractly. Home is where certain people are. Grandma's house is where the biscuits live. The park is where the slide is. Their maps are made of meaning before geometry. Adults do this too, though we dress it in practical language. We say downtown, office, station, favourite cafe, mum's place, old neighbourhood. These labels often point less to coordinates than to roles in our lives. Technology has changed our relationship with place as well. GPS can guide us with astonishing precision. A small device can tell you where you are within meters by comparing signals from satellites thousands of kilometers away. This is extraordinary. It is also slightly humbling that many of us still miss the correct exit while holding such power. Navigation apps reduce one burden, while sometimes weakening another. When constantly guided turn by turn, people may form poorer mental maps. The route is followed but not learned. We arrive without fully knowing where we passed. It is possible to be efficiently transported and mildly absent. By contrast, walking builds richer spatial memory. You notice landmarks, gradients, smells, side streets, the bakery that always smells unfairly inviting, the tree with the bent trunk, the shortcut that saves time but costs dignity in wet weather. Movement through place at human speed teaches place differently. Our ancestors depended on this skill intensely. Foragers, sailors, herders, and travellers learned stars, winds, rivers, terrain, seasons, and subtle cues modern life often lets us ignore. Some indigenous cultures developed navigational knowledge so sophisticated it can astonish contemporary science. Human beings are natural mappers when circumstances ask it of us. Even now, London taxi drivers famously train with demanding route knowledge, and studies have suggested changes in brain regions linked to navigation associated with that expertise. The brain adapts to what it repeatedly does: use maps, build maps, ignore space, outsource space. Then there is the social feeling of being somewhere. A crowded room where nobody knows you can feel less grounding than a tiny kitchen with one trusted friend. Belonging changes location. So does exclusion. This is why phrases like, "I found my place," resonate so strongly. They mean more than coordinates. They mean fit, role, connection, ease. The universe may measure your position mathematically, but human life measures it relationally. You may have noticed that time influences place too. Visit the same street at dawn, noon, rain, snow, festival night, or after years away, and it becomes different each time. Place is never static because light, weather, people, memory and mood keep moving through it. Even your room tonight is not the same room it was this morning. The angle of light changed, temperature changed, sounds changed, you changed. Nothing stays still long enough to be fully pinned down. That includes the body itself. Your cells renew, your posture shifts, your heartbeat pulses. Breathing subtly moves your chest and spine. You're never exactly where you were 1 second ago, even in stillness. At cosmic scales, this becomes even more dramatic, and we will soon return there. But it begins here. The sense of being somewhere is dynamic, not fixed. One more curious fact. Many people can feel phantom vibration from phones that did not vibrate, or reach instinctively for objects no longer in a pocket. This reveals how quickly brains incorporate tools into body maps. A cane, bicycle, car, keyboard, or phone can become extensions of spatial expectation. We do not only locate ourselves in bodies, we locate ourselves through things. That may sound odd, but anyone who has ever patted every pocket while searching for keys already understands the principle. So tonight, as you rest wherever you are, consider the invisible miracle constantly underway. Your brain is stitching sensation into place. It is maintaining orientation, balancing posture, estimating distances, predicting surfaces, holding memories, updating maps, and allowing you the simple comfort of feeling here. All of this so you can lie down and listen to someone calmly discuss coordinates. Science can be wonderfully inefficient that way. Take a slow breath, get comfortable again, and notice something quietly remarkable. You are somewhere so specific that it could, in principle, be described by numbers with extraordinary precision. Not approximately somewhere, not vaguely nearby, not around here somewhere. You occupy an exact location on Earth at this moment, one point among countless others on a moving world. That may not sound dramatic at first. Coordinates rarely arrive with fanfare. They tend to appear as tidy decimals, practical symbols, and the sort of information people ignore until they are lost in a forest, late for dinner, or trying to explain where they parked. Yet coordinates are one of humanity's most elegant inventions. They allow us to take the fuzzy experience of place and turn it into something measurable. They let us say not only that we are on Earth, but precisely where on Earth. They transform here into data, and tonight our task is simple. We begin with your immediate coordinates, right here, right now. If someone asked where you are this second, you might answer with a country, city, or street. That would be useful, but still broad. Imagine saying, I'm in Poland, or I'm in London, or I'm in Chicago. Helpful, certainly, but the universe prefers detail. To narrow your position properly, we need systems. The most famous of these are latitude and longitude, 2 lines of measurement wrapped around the globe. They form a grid that lets any surface point on Earth be identified. It is a little like giving the planet graph paper, only rounder and significantly harder to fold. Latitude tells us how far north or south you are from the equator. Longitude tells us how far east or west you are from the prime meridian, an agreed reference line passing through Greenwich in England. Together they provide an address for almost anywhere on Earth's surface. So if you are listening tonight from Roswell, Tokyo, Nairobi, Toronto, Buenos Aires, or a cabin somewhere that appears on maps only reluctantly, your location can be expressed numerically. That is a profound thing. For most of human history, people knew place locally. They knew the river bend, the mountain ridge, the old road, the tree struck by lightning, the house with the noisy geese. Navigation depended on landmarks, stars, memory, and asking directions from people who may or may not have been feeling helpful. Then gradually, mathematics entered the conversation. Latitude has ancient roots. Long before satellites and smartphones, people noticed that the height of the sun or stars changed depending on where they stood. Sailors could estimate north-south position by measuring celestial angles. It was not effortless, but it worked well enough to cross oceans, discover coastlines, and occasionally arrive somewhere they had not intended. Longitude was trickier. Knowing east-west position requires knowing time. Earth rotates 360 degrees in 24 hours, which means 15 degrees per hour. If you know the local time where you are and compare it with the time at a reference location, you can estimate longitude. Simple in theory. Difficult on a rolling ship with old clocks and questionable weather. This challenge became so important that nations offered prizes for solving it. Eventually, accurate marine chronometers made reliable longitude possible. In other words, some of the greatest navigation breakthroughs came from people deciding clocks needed to behave better. Now let us bring this back to you. At this very moment, you're located by latitude and longitude, but also by elevation. You're not merely at a point across Earth's surface, you're also some distance above or below sea level. Perhaps you're on the 5th floor of a building, perhaps in a valley, perhaps on a hillside, perhaps on a coastal plain where sea level is near enough to matter. If you're in an airplane listening to this, first of all, impressive planning, and second, your coordinates include several kilometers of altitude, so your location is already three-dimensional: latitude, longitude, elevation. But we can go deeper still, because Earth is not a perfect sphere. This may sound rude to Earth, which has worked hard for billions of years, but accuracy matters. Our planet bulges slightly at the equator due to rotation, and is flattened a bit at the poles. The technical term is an oblate spheroid, which sounds less like a planet and more like something a professor might warn students about before an exam. Because Earth is irregular, measuring coordinates precisely requires mathematical models called datums. These define the shape of Earth used for mapping and GPS calculations. Different systems exist, though modern global positioning often uses WGS84, a standardized reference model. This means even saying where you are can depend on which version of Earth you are using mathematically. Science has a wonderful habit of making simple things gloriously complicated. Now imagine opening a map app on your phone. A small blue dot appears. That dot may feel casual, but it represents an astonishing chain of events. Your device receives signals from satellites orbiting Earth. Those signals travel at light speed and contain timing information. By comparing arrival times from multiple satellites, your device calculates distance to each one. With enough measurements, it determines your position. This process is called trilateration. Not triangulation, though people often say that. Triangulation uses angles. Trilateration uses distances. The distinction matters mostly to surveyors, geodesists, and the sort of people who become visibly animated about maps. Your phone can often locate you within meters, sometimes better, sometimes worse if buildings block signals, weather interferes, or you are indoors beneath enough concrete to challenge optimism itself. Still, think about what is happening. Objects in orbit thousands of kilometers above you help identify your place on a spinning planet to a degree ancient navigators would have considered sorcery, and we use this power to locate brunch. Human priorities remain charmingly consistent. Yet immediate coordinates are not only external, there is also your body's position in the room. If you shifted slightly since this began, your coordinates changed. If you rolled onto one side, tucked your feet under a blanket, or adjusted a pillow into a shape best described as emotionally necessary, then your location moved by centimeters or more. Tiny motions count. Even breathing changes coordinate subtly. Your chest rises, your abdomen shifts, the head settles differently against a cushion. Every inhale and exhale redraws your exact geometry in space. Stillness is often movement slowed enough to feel restful. Now let us zoom closer. Suppose we mark the point where the center of your forehead is right now, or the tip of one finger, or the center of mass of your body. Which point truly represents you? This question matters in robotics, biomechanics, and physics. When tracking motion, scientists often define reference points. A runner's stride may be measured using hip markers. A spacecraft's motion may use center of mass calculations. Even where you are depends on what part of you is being tracked. If one hand reaches for water while the rest of you remains settled, part of you travelled while most of you stayed. Identity becomes surprisingly flexible under measurement. Then there is the room itself. You may think of the room as stationary, but buildings expand and contract with temperature. Floors flex under weight. Walls vibrate faintly from traffic, wind, footsteps, heating systems, distant trains, and everyday life. Nothing rigid remains perfectly rigid. At microscopic scales, atoms within the bed, chair, or floor are vibrating with thermal motion. Matter that appears still is alive with activity. So your immediate coordinates are embedded in a restless environment, and Earth beneath that environment is turning. If you're near mid-latitudes, your rotational speed may be around 1,000 kilometers per hour or more relative to Earth's axis. You do not feel it because you, the room, the city, and the atmosphere share the motion. This is one of physics' great comforts. Shared movement feels calm. The same principle lets passengers drink tea on smooth trains, though tea remains famously skeptical during sudden braking. Meanwhile, Earth orbits the Sun. Meanwhile, the solar system moves through the galaxy. Meanwhile, the galaxy moves relative to other galaxies. So your immediate coordinates depend entirely on frame of reference. Relative to your pillow, perhaps stationary. Relative to Earth's center, rotating. Relative to the Sun, orbiting. Relative to the Milky Way, racing onward. Relative to the cosmic microwave background, moving in another measurable way entirely. There is no single universal answer without specifying the frame. This can feel unsettling until it becomes freeing. Location is not one fact. It is a relationship. We see this in daily life too. If someone says, "I'm 5 minutes away," they have given neither distance nor certainty, only optimism. Context matters. Surveyors understand precision in a different way. They can determine positions to centimeters or millimeters using advanced GPS methods, lasers, and careful measurements. Engineers rely on this for bridges, tunnels, buildings, and infrastructure. Tiny errors matter greatly when constructing large systems. A bridge built casually would become memorable for all the wrong reasons. Astronomers, meanwhile, locate observatories with precision because Earth's rotation and shape matter for pointing telescopes accurately. Even looking outward requires knowing exactly where you stand. To know the stars, first know the ground. There is poetry hidden there, though I promise not to overdo such things. Another curious point. Coordinates change over years because continents move. Tectonic plates drift centimeters annually. That means your city is traveling slowly over geological time. Maps are updated, reference frames adjusted. Even the crust beneath familiar streets refuses permanent stillness. Given enough patience, mountain ranges rise, oceans open, and your current address becomes paleontological gossip. Tonight, though, we stay with the present. You're in one room, one building perhaps, one neighborhood, one city, one nation, one latitude band, one time zone, one atmosphere layer close to the surface, one weather pattern, one rotating hemisphere under a particular night sky. That is already an immense amount of specificity. The phrase "I'm here" carries more information than it seems, and there is something soothing in that. Large cosmic questions can make us feel small or vague, but coordinates remind us that existence is not blurry. You're not lost in abstraction. You're somewhere definite, a precise point in space, a real moment in time, a measurable presence. Your body has weight because gravity reaches you here. Air pressure surrounds you here. Temperature touches skin here. Sound arrives here. Light lands in your eyes here. Consciousness is happening here. Whatever else the universe may be, this point matters because you are occupying it. Beneath your feet, beneath the floorboards or concrete, beneath carpet, tile, wood, soil, stone, roots, pipes, foundations, and everything built by human hands, there is a planet. We say that so casually that it almost disappears into ordinary language: the ground, the earth, the land. But the surface supporting you tonight is not just ground in the everyday sense. It is the outer skin of a world 12,742 kilometers wide, layered, heated within, weathered above, ancient beyond easy comprehension, and carrying every city, forest, road, memory, and sleeping person through space. You're not resting on something small. You're lying on the uppermost edge of a planetary body formed around 4.54 billion years ago from dust and debris orbiting a young sun. Long before streets existed, before oceans as we know them, before trees, birds, whales, bread, bicycles, or mildly disappointing software updates, matter in the early solar system collided, merged, heated, and gathered. Gravity patiently pulled fragments together. Larger bodies grew, smaller ones struck them. The young Earth was not a calm blue marble. It was a violent construction site. If planets could complain, the early Earth would have had grounds to do so. During its youth, impacts were common. Rock melted, surfaces reformed. Heavy elements like iron sank inward toward the centre. Lighter materials rose. Over immense spans of time, Earth differentiated into layers: crust, mantle, outer core, inner core. This structure still defines the world beneath you now. Most of us live our lives interacting only with the thinnest part of that system. The crust is the outer shell, the layer where mountains rise, rivers flow, roots spread, cities stand, and people misjudge weather forecasts. Compared with the whole planet, the crust is surprisingly thin. Oceanic crust may be around 5 to 10 kilometers thick. Continental crust can reach 30 to 70 kilometers in some places. That sounds thick until you compare it with Earth's radius of over 6,300 kilometers. If Earth were the size of an apple, the crust would be thinner than its skin. Everything familiar to human civilization exists on that narrow surface zone. Every empire, every library, every concert, every argument in traffic, every lullaby, every telescope, every loaf of bread, every missed train, every love letter, every cat convinced it owns the house, all of it on the planetary skin. Below the crust lies the mantle, extending nearly 2,900 kilometers downward. Despite sounding dramatic, the mantle is mostly solid rock, though over long timescales it flows slowly. Not like water, not like syrup, more like extremely hot rock behaving plastically under pressure across millions of years. This slow movement matters enormously. The mantle helps drive plate tectonics, the grand rearrangement of Earth's surface. Continents drift, ocean floors spread, mountains rise, volcanoes erupt, earthquakes shake, coastlines change. Entire oceans open and close over geologic time. The world map is temporary. It may feel permanent because our lives are brief relative to tectonic motion, but the continents are not frozen in place. Africa moves northward. The Atlantic widens. The Pacific changes. India once travelled north and collided with Asia, helping raise the Himalayas. The Mediterranean is the remnant of older oceans. Land remembers collisions we never witnessed. Your current address sits on a tectonic plate. That plate may be Eurasian, African, North American, South American, Pacific, Antarctic, Indo-Australian, or one of several smaller plates. These enormous slabs of lithosphere move centimeters per year, slow enough to ignore daily, powerful enough to reshape worlds. So even while resting, you are drifting geologically. It is one of the quieter forms of travel. Deeper still lies Earth's outer core, a liquid layer composed mainly of iron and nickel. It swirls around the inner core and helps generate Earth's magnetic field through motions of electrically conducting fluid. This magnetic field extends into space and shields the planet from much of the solar wind, streams of charged particles flowing from the sun. Without that protection, Earth's atmosphere and surface conditions might be very different. Your peaceful evening owes something to molten metal thousands of kilometers below you. That is not a sentence people use often enough. At the center lies the inner core, solid despite extreme heat because pressure there is immense. Temperatures may rival the surface of the Sun, yet iron remains solid under crushing force. The deepest interior is inaccessible directly. No drill has come remotely close. Our understanding comes from seismology, experiments, and physics. When earthquakes happen, seismic waves travel through Earth differently depending on the materials they cross. By measuring those waves, scientists infer internal structure. In other words, we learned much about the hidden center of the planet by listening to vibrations. The Earth has always rewarded careful listeners. Now consider the surface beneath you in local terms. If you're in a city, the land may be filled, leveled, paved, tunneled, reinforced, and layered with generations of construction. Beneath streets may lie old roads. Beneath those, older foundations. Beneath them, sediments or bedrock formed in environments no human ever saw. If you are inland, your ground may once have been ocean floor. If coastal, sea levels have risen and fallen repeatedly across ice ages. If mountainous, your landscape may owe its height to collisions deep in geologic history. If on plains, perhaps ancient rivers laid the sediments. If near glaciers in the distant past, ice may have scraped, carved, and shaped the terrain long before your building arrived. Every floor rests on a story. Soil itself is a marvel often treated like dirt in both senses of the word. It forms slowly from weathered rock, organic matter, water, microorganisms, fungi, roots, and time. Healthy soil supports agriculture, ecosystems, forests, and much of civilization. A thin, fertile layer can feed millions. Civilizations rise on topsoil more than they realize. Then there is groundwater, moving invisibly through pores and fractures beneath the surface. Aquifers store fresh water accumulated over years, centuries or longer. Wells tap it. Springs reveal it. Entire communities depend on hidden reserves beneath the land. Below many feet tonight, water may be travelling quietly through stone. The planet is busy even when it looks still. Surface calm can hide immense motion. Magma chambers shift. Stress builds along faults. Rivers erode grain by grain. Roots pry into cracks. Microbes transform minerals. Frost expands fractures. Sediments settle. Wind transports dust. Rain dissolves and shapes. Nothing is static for long. Even the shape of land responds to weight. During ice ages, massive ice sheets depressed crust downward. When the ice melted, some regions began slowly rebounding upward, a process still continuing today. The ground can rise centuries after glaciers depart. Earth remembers pressure. Gravity also varies slightly from place to place depending on altitude, geology, and Earth's shape. You weigh a tiny bit less atop mountains than at sea level, partly because you are farther from Earth's centre. Mass concentrations in crust and mantle create additional subtle differences, so the planet beneath you influences not only scenery, but your exact weight. Use this information responsibly. Mountains themselves are not permanent. They rise through tectonic uplift and wear down through erosion. The Himalayas continue to rise in places while rain, rivers, frost and gravity work to reduce them. Landscapes are negotiations between forces that build and forces that wear away. Coasts shift similarly. Waves erode cliffs. Sediment forms beaches. Storms redraw shorelines overnight. Sea level changes over time. Deltas grow and shrink. Barrier islands migrate. What seems fixed in a holiday photo may be transient in geology. This matters because human maps often imply certainty where nature prefers revision. The atmosphere above you is part of the planet too. Earth is not only rock and metal. It is wrapped in gases held by gravity, mostly nitrogen and oxygen, with trace components that matter enormously. This thin envelope moderates temperature, carries weather, enables breathing, scatters blue light across daytime skies, and burns many incoming meteoroids before they reach the ground. You live at the bottom of an ocean of air. We rarely feel how deep it is because we are adapted to it. But air has weight. Pressure surrounds you now, pushing gently from all directions. At sea level it's substantial, though balanced by your body so naturally that it goes unnoticed. Weather is the atmosphere's restless personality. Wind, rain, clouds, heat waves, snow, fog, storms, and calm all arise from solar energy interacting with rotating Earth, oceans, land, and fluid dynamics far more complex than many forecasts politely admit. Meanwhile, oceans cover about 71% of the surface. They regulate climate, absorb heat, circulate nutrients, shape weather, host ecosystems, and store immense history. Marine sediments preserve records of past climates and extinctions. Tides rise and fall under lunar and solar gravity. Even if you are far from the sea tonight, oceans influence your life. Now let us scale back to something intimate again. The exact spot beneath you may be concrete poured from crushed rock and cement, or timber once grown from sunlight and rain, or steel refined from ore mined out of older stone, or bricks fired from clay. Human structures are rearranged geology, cities are minerals with paperwork. Your bed frame, walls, glass, electronics, wiring, ceramics, paints, and plumbing all trace back to materials drawn from Earth. Even refined technologies begin as rock, metals, sand, and chemistry. We often imagine ourselves apart from nature while resting inside transformed crust. And through all this, the planet rotates. One turn roughly every 24 hours. You're carried eastward or westward depending on perspective through day and night. If dawn is hours away where you are, Earth is already turning you toward it. No sunrise rushes toward us. We rotate into light. This simple reversal changes the feeling of morning. The planet also orbits the Sun, as we discussed before, carrying its atmosphere, oceans, mountains, cities, and listeners onward through space. The solidness beneath you is real, but so is the motion. There is comfort in that combination. Stable enough for life, dynamic enough for change. Earth may be the only world we know with plate tectonics operating as it does. Large surface oceans, abundant life, breathable air, and a biosphere complex enough to wonder about itself. Other planets are fascinating. Some are majestic. Some are violent. Some are beautiful in harsh ways. But the ground beneath you tonight is rare by every measure currently available. That does not mean perfect. Earthquakes happen, volcanoes erupt, storms strike, climate shifts, nature can be severe. Yet across billions of years, this world has sustained continuity enough for evolution to produce forests, whales, fungi, coral reefs, human language, and whoever first decided bread should be sliced. An extraordinary record. Sometimes cosmic thinking makes people feel small, but there is another way to see it. You're not merely on a tiny dot. You're on a deeply complex, active, life-bearing planet with a molten heart, moving plates, protective magnetism, cycling water, breathing atmosphere, and a surface capable of consciousness. That is a remarkable flaw. It feels still, doesn't it? The room is quiet. The bed, chair, or sofa beneath you seems dependable. Walls hold their places with admirable professionalism. A cup on the table remains where it was left. Curtains hang without dramatic concern. Nothing in ordinary experience suggests that you are currently moving at extraordinary speed. And yet, you are. Right now, as you listen, Earth is spinning, orbiting, drifting, and carrying you through several layers of motion all at once. The stillness you feel is real in one sense, but only because you and everything around you are sharing the journey together. Tonight, we step into one of science's gentlest surprises. Motion can feel exactly like rest. Let us begin with the spin. Earth rotates once approximately every 24 hours. This daily turn creates sunrise, sunset, noon, midnight, and the familiar rhythm by which alarms are resented and weekends are cherished. We often speak as if the sun moves across the sky, but in practical truth, Earth turns and brings different regions into sunlight. Morning is not something that arrives. We rotate into it. That simple idea changes perspective. Dawn is the moment your part of the planet turns toward the sun again. Night is what happens when your location turns away. Day and darkness are not events happening above us so much as consequences of planetary motion beneath us. How fast is this spin? At the equator, Earth's circumference is about 40,075 kilometers. Divide that by roughly 24 hours, and a point on the equator moves at around 1,670 kilometers per hour due to rotation. That is faster than many commercial aircraft. If you are not at the equator, your speed is lower, because you travel a smaller circle around Earth's axis. The farther north or south you are, the smaller that circle becomes. Near the poles, rotational speed drops dramatically. At the exact pole, you would rotate in place rather than sweep around a wide circle, so depending on where you live, you are moving quickly, very quickly, or in a highly specialized manner, yet you do not feel any of it. Why not? Because sensation responds strongly to changes in motion, not steady motion itself. If a train glides smoothly at constant speed, and the ride is calm, passengers may forget movement entirely until someone walks by carrying tea and confidence. Likewise, Earth's rotation is steady and shared by you, the atmosphere, your furniture, the oceans, and the city around you. There is no sudden shove each morning as the planet starts turning. It has been turning all along. This principle was difficult for many earlier thinkers to accept. If Earth moved, surely we would notice. Surely birds would be left behind. Surely towers would lean dramatically. Surely hats would become impossible. But physics had a calmer answer. Shared motion hides itself. If you toss a ball upward inside a smoothly moving ship, it returns to your hand rather than smashing into the stern in protest. The ball already shares the ship's horizontal motion. In the same way, the air, clouds, birds, and all of us share Earth's rotation. The planet spins together. There are effects of rotation, however. They are subtle in daily life but important globally. One is the Coriolis effect, an apparent deflection of moving objects across a rotating surface. It influences large-scale wind patterns, ocean currents, and storm rotation. In the northern hemisphere, moving air tends to curve one way, in the southern hemisphere the other. This does not determine the direction your sink drains in ordinary bathrooms, despite many confident legends. Plumbing is often more influential than planetary mechanics. Earth's rotation also causes equatorial bulging. Because spinning bodies experience outward effects relative to the axis, Earth is slightly wider at the equator than pole to pole. Our planet is not a perfect sphere. It is an oblate spheroid, which sounds formal enough to be invited to conferences. Rotation even affects weight slightly. At the equator, the outward effect of spin reduces apparent weight a tiny bit compared with the poles. So if you have ever wanted a scientific excuse for minor scale differences, geography offers one. Now let us add the next layer. While Earth spins daily, it also orbits the Sun yearly. Our planet travels around the Sun once every approximately 365.25 days, following an elliptical path that is close to circular. The average orbital distance is about 150 million kilometers, known as 1 astronomical unit, and the speed, around 107,000 kilometers per hour. That means every second, Earth moves nearly 30 kilometers along its orbit. By the time you read a sentence slowly, the planet has gone farther than many people drive to work. Still no rushing sensation. Still no cosmic breeze through the curtains. Again, because you, the atmosphere, and everything near you share the motion. This orbit is one reason seasons exist, though not because Earth gets dramatically closer or farther from the Sun in summer and winter. The real cause is axial tilt. Earth's axis leans about 23.5 degrees relative to its orbital plane. As Earth travels around the Sun, different hemispheres receive sunlight at different angles and durations during the year. So summer is not closer to the Sun. It is your hemisphere leaning toward it. that tilt shapes agriculture, ecosystems, migration, daylight hours, cultural calendars, holiday traditions, wardrobes, and annual complaints about weather. It is difficult to overstate how much human life depends on a slight lean. Imagine Earth without tilt. Seasons would weaken greatly. Many climate patterns would differ. Biological rhythms, farming systems, and human history itself might look very different. A tilted, spinning, orbiting world has consequences. Now let us zoom outward once more. The Sun itself moves through the Milky Way galaxy. Our star, along with all its planets, asteroids, comets, dust, and whatever is currently misplaced in your kitchen drawer, orbits the galactic centre at roughly 828,000 kilometers per hour. One complete orbit around the galaxy takes about 225 to 250 million years. This is sometimes called a cosmic year. When dinosaurs walked Earth, the solar system was in another region of the galaxy. Since the earliest mammals appeared, we have travelled vast arcs around the Milky Way without noticing, and the galaxy moves too. The Milky Way and nearby galaxies interact gravitationally, drift within larger structures, and move relative to the cosmic microwave background, the faint afterglow of the early universe. Measurements suggest our local group of galaxies moves hundreds of kilometers per second relative to that frame. So where are you right now? Relative to your pillow, mostly still. Relative to Earth's axis, rotating. Relative to the Sun, orbiting. Relative to the galaxy, racing onward. Relative to larger cosmic frames, moving differently again. There is no single speed that answers everything because motion depends on reference frame. This can sound frustrating until it becomes liberating. Physics is not withholding certainty out of spite. It is telling us that movement is relational. You are always moving compared with something and calm compared with something else. This truth appears in everyday life too. A person standing in a train may be still relative to the carriage, moving relative to the station, and perhaps emotionally unsettled relative to their schedule. Frames matter. Now consider what Earth's motion does for life. Rotation creates day-night cycles that shape circadian rhythms in plants, animals, fungi, and people. Our sleep hormones, body temperature patterns, and alertness cycles are deeply tied to light and dark. The turning planet regulates biology. Orbit provides a yearly pattern of seasons and solar angles, influencing migrations, breeding cycles, plant growth, monsoons, and agriculture. Entire civilizations organize calendars around these predictable motions. Motion creates rhythm, and rhythm creates habit, biology, culture, expectation. Even language carries this inheritance. We speak of sunrise and sunset though we know Earth rotates. We say the sun rises because human experience values appearances first and mechanics second. This is understandable. Saying the sun appears due to planetary rotation bringing our longitude into line of sight lacks the warmth of morning. There are tiny irregularities too. Earth's rotation gradually slows over immense timescales, due mainly to tidal interactions with the moon. Long ago, days were shorter. Hundreds of millions of years ago, a year contained more days because each day lasted fewer hours. Imagine explaining that to someone annoyed by Monday. The moon itself slowly recedes from Earth as tidal forces transfer angular momentum. Our planet and its companion are in a long gravitational dance, subtly reshaping one another over time. Nothing in celestial mechanics remains frozen. Even leap years exist because Earth's orbital period is not an integer number of days. Our calendars must occasionally adjust to keep civil time aligned with seasonal reality. Human systems are forever trying to negotiate with astronomical facts. Sometimes we win, sometimes we invent more paperwork. Now return to your immediate surroundings. The cup on the table is moving with Earth. The table is moving. The building is moving. The city, forests, rivers, mountains, clouds, oceans, birds, and sleeping neighborhoods are all traveling together. You're not a stationary observer watching the universe pass by. You're a passenger inside it. There is comfort in shared travel. We often imagine ourselves isolated. each person carrying private concerns through narrow routines. But physically, every person alive tonight is aboard the same spinning world. Billions of us are crossing darkness together, whether awake, dreaming, working late, caring for children, studying, laughing, grieving, or quietly listening. Same planet, same voyage. Sometimes people ask whether motion through space should create wind or friction, but space is mostly empty. There is no ordinary air for Earth to rush against in orbit. Motion through vacuum is not like driving with windows down. Cosmic travel is quieter than many commutes. Another question: if Earth moves so fast, why do stars look fixed? Because they are extremely distant. Their apparent positions shift slowly, though careful measurements reveal stellar parallax and proper motion. Over enough time, even constellations change shape. The sky seems stable partly because our lives are short relative to celestial rearrangement. Given millennia, the heavens redraw themselves. Tonight, however, they remain familiar enough to reassure. One more subtle thought: stillness may be less fundamental than we imagine. In the universe, rest is usually local. A bench can be at rest relative to the park, but the park is not at rest relative to Earth's centre, nor Earth to the Sun, nor the Sun to the galaxy. Absolute stillness is elusive. What we call stillness is often successful agreement. That may be useful beyond physics. Peace in life is not always the absence of movement. Sometimes it is moving steadily within something larger that holds together. For now, as you settle deeper into comfort, know this: the calm you feel is genuine, even while you travel at astonishing speed. There is no contradiction there. The room is quiet, the planet is turning, the star system is moving, the galaxy is gliding, and you are resting beautifully through all of it. Look upward on a clear night, and there it is again. Sometimes bright and round, sometimes thin and careful at the edge of twilight, sometimes pale in daylight like it forgot to leave on time, sometimes hidden entirely, though never truly gone. The moon has a way of appearing familiar no matter how little attention we give it. It asks for almost nothing, says nothing at all, and yet has accompanied Earth through nearly all of our planet's story. Tonight, as our world spins and travels onward, we turn to its oldest visible companion. The moon is so woven into human life that it can seem ordinary. We place it in children's books, poems, calendars, songs, symbols, and sleepy metaphors. We glance at it through windows, mention it casually, photograph it badly with phones, and move on. Yet the moon is an extraordinary object, and its quiet presence has shaped Earth more deeply than many realise. It is not merely nearby scenery, it is part of why Earth is the world we know. Let us begin with distance. On average, the moon orbits about 384,400 kilometres from Earth. In cosmic terms, that is close. In practical terms, it is far enough that light takes about 1.3 seconds to travel between us, and spacecraft require days rather than moments to arrive. If Earth were the size of a basketball, the moon would be a tennis ball roughly 7 meters away. That empty space between them is important. Diagrams often compress reality until celestial bodies look cozy and sociable. In truth, space prefers elbow room. The moon itself is about 1/4 the diameter of Earth. That makes it unusually large relative to its planet compared with many other moon-planet pairings in the solar system. Some worlds have moons that are tiny pebbles by comparison. We have one substantial companion. This ratio matters. The leading theory of the moon's formation suggests that long ago, early Earth collided with a Mars-sized body often called Theia. The impact was catastrophic by any ordinary standard, which is to say it would have been very difficult on nearby property values. Vast amounts of material were thrown into orbit. Over time, debris gathered and formed the moon. A violent beginning led to long stability. Science often contains these surprising combinations. Imagine early Earth glowing hot, reshaped by impact, while a new moon gradually assembled from surrounding debris. No oceans yet as we know them, no forests, no birdsong, no sleepy listeners, just molten rock, gravity, time, and the patient mechanics that eventually gave rise to a sky where the moon could hang quietly over rooftops. And once formed, the moon began influencing Earth immediately. Its gravity pulls on our planet, especially the oceans, producing tides. Water bulges slightly on the side facing the moon, and also on the far side due to the dynamics of the Earth-Moon system. As Earth rotates through these bulges, coastlines experience rising and falling seas. Tides are not just scenic timing for beach walks. They mix coastal waters, shape ecosystems, transport nutrients, influence marine life cycles, and historically aided navigation and fishing. Entire species live by tidal rhythms. Human communities have long planned around them. Even now, harbours, shipping, flood risk, and shoreline life remain tied to the moon's pull. There is something lovely about that. A body hundreds of thousands of kilometres away lifts oceans without touching them. The moon has another crucial role, stabilising Earth's axial tilt. Remember that Earth leans by about 23.5 degrees, giving us seasons. Without a substantial moon, simulations suggest Earth's tilt might vary much more chaotically over long timescales. Wild shifts could create dramatic climate changes across geological eras. The moon acts as a gravitational moderator, helping keep Earth's wobble comparatively stable. In other words, our companion helps steady the climate stage on which life evolved. This does not mean the moon solves every problem politely, but it has likely made Earth a more stable home than it otherwise would have been. Then there is rotation. Long ago, Earth spun faster. Days were shorter, perhaps much shorter. Through tidal interactions, the moon has gradually slowed Earth's rotation over immense timescales. Friction in oceans and crust transfers angular momentum, causing days to lengthen while the moon slowly recedes outward. So the moon both slows our spin and drifts away. At present, it moves farther from Earth by about 3.8 centimetres per year, roughly the speed fingernails grow. A delicate cosmic separation measured with lasers bounce from reflectors left by Apollo missions. Yes, humans placed mirrors on the moon and now use them to measure distance changes with exquisite precision. It is difficult not to admire that sentence. The slowing of Earth's rotation means that hundreds of millions of years ago, days were shorter. Coral growth patterns and geological evidence suggest more days fit into a year because each day contained fewer hours. Imagine a future office worker learning that prehistoric Mondays arrived more frequently. The moon itself keeps one face turned toward Earth. This is called tidal locking. The moon rotates on its axis in the same time it takes to orbit Earth, so we always see nearly the same hemisphere. This led generations to speak of the dark side of the moon, though that phrase is misleading. The far side receives sunlight just as the near side does. It is simply the side not visible from Earth. The far side remained unseen by humans until the space age. Think about that. For most of history, half the moon was hidden from direct human view. A familiar object still held secrecy. When spacecraft finally photographed the far side, it revealed a landscape different from the near side, more heavily cratered, fewer dark maria, and a rougher appearance. Even neighbours have private faces. The dark plains visible on the near side, called maria, were once mistaken for seas. Early astronomers named them with poetic seriousness: sea of tranquility, sea of rains, ocean of storms. In truth, they are ancient lava plains formed billions of years ago after impacts opened basins later filled by volcanic flows. The moon's surface tells a history of violence now wrapped in stillness. Because it lacks weather, flowing water, and substantial atmosphere, footprints and craters can persist for immense spans. There is no wind to erase much of anything. Disturb the lunar dust, and the mark may remain for ages. Earth constantly renews itself. The moon remembers. That contrast is striking. On Earth, rain softens edges, plants break stone, Rivers carve valleys, glaciers scrape, tectonics recycle crust. Here, surfaces are temporary. There, change is slow and sparse. Perhaps that is one reason the moon can feel calm. It wears old scars without fuss. Human culture has long responded to lunar cycles. The month itself traces back to the moon's phases. Many calendars rely partly or wholly on lunar motion. Festivals, planting traditions, religious observances and navigation practices have followed its schedule. The moon offered one of humanity's earliest clocks. No batteries, no notifications, reasonably reliable. Its phases arise from geometry. Half the moon is always sunlit. What changes is how much of that illuminated half we can see from Earth as the moon orbits us. New moon occurs when the moon lies roughly between Earth and Sun. Full moon when Earth lies roughly between Sun and Moon. Crescents, quarters, gibbous phases all emerge naturally from angles and light. There is elegance in that. The changing face is not the moon changing mood, it is perspective changing shape. Still, many people feel the phases emotionally. A full moon often seems larger, brighter, somehow meaningful. Some of this is cultural expectation. Some is the simple power of bright light in darkness. Some is the moon illusion, where the moon near the horizon appears larger because of how our brains interpret scenery and distance. Brains, once again, are enthusiastic collaborators in experience. Moonlight itself is sunlight reflected from lunar rock. Soft, silver, gentle to us, but fundamentally borrowed daylight. The moon glows not by making light, but by returning it. There may be a lesson in that, though I promise to keep abstractions under control. The moon has guided travellers too. Before electric cities dimmed the stars, moonlit nights could transform landscapes. Roads, coastlines, fields and paths became navigable under lunar brightness. Farmers, sailors, herders and wanderers all knew the value of a bright moon. Even animals use it. Coral spawning, predator-prey behaviour, insect movement, migration patterns, and many biological rhythms respond to lunar cycles. Life notices companionship. Then came the era of direct exploration. In 1969, humans first set foot on the moon. The Apollo missions turned a distant symbol into a visited place. Rocks were collected, experiments deployed, horizons stood black against stark light. Earth rose in lunar skies as a blue world hanging in darkness. Few images have altered perspective more than seeing Earth from the moon. From there, our world appears whole, borderless, delicate, finite. Many astronauts described profound emotional responses. Distance can sharpen love. Since Apollo, robotic missions from multiple nations have orbited, landed, crashed occasionally with enthusiasm, and studied the moon in increasing detail. Water ice in permanently shadowed polar craters appears likely. That matters scientifically and practically for future exploration. Even now, the moon remains active in human plans. Bases are discussed, resources considered, science goals expanded. The old companion may become a stepping stone deeper into space. Yet tonight, it is enough simply to know it is there. Whether clouds cover it or not, whether it is waxing, waning, full or hidden in daytime glare, the moon continues its orbit. It circles Earth roughly every 27.3 days relative to the stars, and about 29.5 days from new moon to new moon, because Earth also moves around the Sun. Nothing dramatic is required, it simply keeps going, and perhaps that is why the moon feels comforting. It is regular without being rigid, familiar without being dull, present without demanding attention, there through childhood windows, there above late-night walks, there over oceans, there above cities that forgot to look up, there over villages that still do. While Earth spins and carries us onward, the moon travels with us, bound by gravity shaping tides, steadying tilt, lengthening days, and reflecting sunlight into countless human nights. A quiet companion, yes, but not a passive one. Once we step beyond Earth and its faithful moon, the view changes quickly. Our familiar world, so large in daily life, begins to shrink into one member of a much broader family. Mountains become invisible. Oceans blend into colour. Borders vanish entirely. Even the moon, whose presence has guided tides and calendars for ages, becomes simply Earth's nearest companion in a much larger neighbourhood. Tonight, we widen the map again. We are no longer asking only where you are on Earth, or where Earth is relative to the moon. We are asking where our world belongs within the solar system itself, and to answer that, we need to understand the structure of the place we call home in space. The solar system is centred in a practical gravitational sense around the Sun, the star whose light and energy sustain nearly everything familiar to us. Around it move planets, dwarf planets, moons, asteroids, comets, dust, magnetic fields, and streams of charged particles. It is not arranged like a tidy classroom diagram with perfectly spaced circles and labels. It is dynamic, spacious, and somewhat messier than textbooks politely suggest. Still, there is order within that mess. At the centre is the Sun, containing more than 99.8% of the solar system's mass. That means nearly everything gravitationally important is concentrated in one star. The planets, impressive as they may seem to us, are comparatively small leftovers orbiting the main event. If the solar system were a company, the Sun would own almost all the shares. Closest to the Sun are the inner rocky planets, Mercury, Venus, Earth, and Mars. These are the terrestrial planets, built largely from rock and metal, smaller and denser than the outer giants. They occupy the warmer inner region of the solar system where lighter gases were less easily retained during formation. Then comes a broad region populated by countless rocky remnants, the asteroid belt. Beyond that lie the gas and ice giants, Jupiter, Saturn, Uranus, and Neptune. Farther still are icy bodies, dwarf planets, and the distant reservoirs of comets. So, where are we? Earth is the third planet from the Sun. That simple fact is one of the most important addresses in science. Not first, where conditions are harshly hot. Not fifth, where giant worlds dominate. Third, a location where liquid water can exist on the surface, where temperatures can support long-term chemistry useful for life, and where sunlight arrives in generous but not overwhelming amounts. We orbit in what is often called the habitable zone, a region around a star where surface temperatures may allow liquid water under the right atmospheric conditions. This does not guarantee life, but it creates opportunity. Earth occupies fortunate real estate. That said, fortunate in astronomy is usually shorthand for a long chain of physical circumstances rather than cosmic favoritism. The universe did not reserve us a seat. Conditions happened to allow one. Let us move through the neighbourhood slowly. Closest to the Sun is Mercury, a small rocky world with dramatic temperature swings. One side can become intensely hot in sunlight, while darkness brings severe cold. With little atmosphere to soften extremes, Mercury lives a stark existence. Then comes Venus, similar in size to Earth, but radically different in character. Thick clouds hide a surface hot enough to melt lead, with crushing atmospheric pressure and a runaway greenhouse effect that turned a near twin into a warning. Third is Earth, blue with oceans, active weather, moving plates, breathable air, and one species asking detailed questions at bedtime. Fourth is Mars, colder and thinner-aired, home to giant volcanoes, ancient river evidence, dust storms, and decades of scientific attention. Mars often feels like the solar system's what-if world. What if conditions had gone differently there? Beyond Mars lies the asteroid belt, though belt can be misleading. It is not a crowded obstacle course requiring dramatic spaceship maneuvers. Objects are widely separated. Space, as always, enjoys leaving room. The largest body there is Ceres, classified as a dwarf planet. Many smaller asteroids are relics from planetary formation, material that never became a full world. Then comes Jupiter. Jupiter is the giant of the family, massive enough to dominate surrounding gravitational dynamics. It has dozens of moons, immense storms, powerful radiation belts, and a magnetic field of impressive scale. Some scientists argue Jupiter's presence influenced the architecture of the entire solar system. If planets held reunions, Jupiter would arrive early and occupy most of the room. After Jupiter comes Saturn, famed for rings so elegant they almost seem fictional. Yet those rings are real, composed largely of ice particles and debris ranging from tiny grains to sizable chunks. Saturn too has many moons, including Titan, with thick atmosphere and methane lakes. Then Uranus, tilted dramatically on its side, rotating in a manner that always seems slightly theatrical. Its seasons are extreme because of that tilt. Then Neptune, deep blue and windy, orbiting far from the Sun in cold outer darkness. Even there, atmospheric activity remains vigorous, and beyond Neptune the solar system continues. There is the Kuiper Belt, a region of icy bodies including Pluto, Haumea, Makemake, and others. Farther still may lie the distant Oort cloud, a vast hypothetical reservoir of comets extending astonishing distances outward. So when we say our place in the solar system, Earth is not near the edge, nor at the centre, nor isolated. We are part of the inner planetary region, among rocky worlds, between Venus and Mars. That position has consequences. Jupiter's gravity farther out may have helped reduce some impact threats while also perturbing others. The asteroid belt remained a belt rather than becoming a planet, partly because Jupiter's gravity stirred it. Outer giants shaped migration histories and scattering events during early solar system evolution. Inward, Venus reminds us how climate can diverge drastically. Outward, Mars hints at lost possibilities. Around us, the moon stabilizes our tilt. Our place is meaningful partly because of what surrounds us. Location is relationship. Earth also orbits within the ecliptic plane, the flattened general plane in which most planets move because they formed from a rotating disk of gas and dust around the young sun. This shared alignment means the solar system carries memory of its birth. Even billions of years later, the architecture still reflects formation history. The planets do not orbit in perfect circles. They trace ellipses. They tug on one another slightly. Resonances occur. Small bodies are perturbed. Comets dive inward, then vanish outward again. Space may look serene from diagrams, but celestial mechanics is a living dance of gravity. And Earth participates fully. Every year, our world completes one orbit. Seasons cycle because of tilt. The night sky shifts. Constellations visible at midnight in winter differ from those in summer, because we stand at another part of Earth's path around the Sun. This means your seasonal sky is a map of orbital progress. If you have ever noticed certain constellations returning each year, you have quietly observed planetary motion. Now consider scale emotionally rather than numerically. Daily life can make Earth feel central because it is central to us. Understandably so. Bills, breakfasts, weather, relationships, schedules, and local inconveniences all happen here. But in the solar system, Earth is one world among many. That does not diminish it. Being one among many can increase appreciation. Earth is not less special because other planets exist. It becomes more interesting because comparison is possible. We can study why Venus became hostile, why Mars dried, why giant planets formed far out, why moons vary so wildly, why rings persist, why atmospheres differ. Neighbours help define home. We have also sent ambassadors of a sort. Robotic spacecraft have visited every major planet. Landers touched Venus and Mars. Orbiters mapped worlds in detail. Probes flew past Jupiter, Saturn, Uranus, Neptune, Pluto. Rovers crossed Martian ground. The Voyager 1 and Voyager 2 spacecraft now travel beyond the main planetary region, carrying traces of us outward. Our curiosity has already left the driveway, and still, for all this exploration, Earth remains the only confirmed inhabited world. No other planet yet shows forests, cities, laughter, bread ovens, thunderstorms over suburbs, or someone listening quietly while falling asleep. That makes our address within the solar system scientifically ordinary in one sense, but precious in another. There is also a practical lesson in knowing our place. Solar storms from the sun can affect satellites, power systems, and communications. Near-Earth asteroids are tracked because location matters for safety. Planetary science informs climate understanding. Studying Mars and Venus helps us understand Earth better. The neighbourhood is not just scenery, it is relevant. Tonight, if you imagine looking down from far above the solar system, you would see no highlighted marker reading "You are here." There would be a bright sun, faint moving worlds, and one small blue planet tracing a path in the third lane from the centre. On that planet, somewhere across oceans and continents, one listener resting under a roof. That is enough precision for now. People often learn the solar system in a neat and friendly way. A bright sun in the middle, planets arranged in order, circular paths around them, names memorised in school, perhaps a model made from foam balls hanging by string, each world politely close enough to fit above a classroom radiator. It is charming. It is also wildly misleading. Not because the order is wrong, but because the scale is compressed beyond recognition. The true solar system is defined less by planets themselves and more by the astonishing emptiness between them. Once distance is restored, everything changes. Worlds become tiny islands. Orbits become broad, lonely tracks. Space stops feeling crowded and begins to feel vast. Tonight we slow down and let the real size of our neighbourhood sink in. At the centre sits the Sun, containing almost all the solar system's mass. Its diameter is about 1.39 million kilometres. Around it orbit the planets at distances so large that ordinary intuition struggles to keep up. Our daily minds evolved for rooms, fields, roads, rivers, and perhaps the occasional hill. They did not evolve for millions of kilometres, so let us build scale carefully. The average distance from Earth to the Sun is about 150 million kilometres. This distance is called 1 astronomical unit, or AU. It is a useful measuring stick for the solar system because using kilometres repeatedly becomes exhausting rather quickly. 1 AU is the baseline. Earth orbits at 1 AU. Mercury averages about 0.39 astronomical units from the Sun. Venus about 0.72 astronomical units. Mars about 1.52 astronomical units. Jupiter around 5.2 astronomical units. Saturn 9.5 astronomical units. Uranus 19.2 astronomical units. Neptune about 30 astronomical units. Already the outer planets feel remote, but numbers alone can slide past the mind. So let us shrink the solar system into something human-scaled. Imagine the Sun as a large front door about 2 meters tall. On that scale, Earth would be smaller than a peppercorn, roughly 22 meters away. Not next to the door, not in the hallway, 22 meters away. A peppercorn orbiting a door. Jupiter, much larger than Earth, would still only be around the size of a grape, but it would sit over 100 meters away. Neptune would be hundreds of meters farther still. Pluto, if included, would be nearly a kilometer away, tiny and cold. And between these objects, mostly nothing. That is perhaps the most important lesson of scale. Space is spacious. Science fiction often depicts spacecraft weaving constantly through nearby planets, asteroids, stations, and dramatic hazards. Real travel is more patient. Long stretches of emptiness separate destinations. A ship crossing the solar system would spend much of its time surrounded by dark, distance, and mathematics. Even the asteroid belt, often imagined as a dense obstacle field, is mostly empty space. Asteroids are spread so widely that collisions are rare. A spacecraft crossing the belt is not dodging rocks every minute. It is usually passing through vast emptiness with occasional company. Reality is less cinematic and more enormous. Now let us consider light. Light travels at about 300,000 kilometers per second. fast enough to circle Earth more than 7 times in 1 second. To us, it seems instant. Yet in the solar system, even light needs time. Sunlight takes about 8 minutes and 20 seconds to reach Earth. When you feel sunlight on your skin, that energy began its journey over 8 minutes earlier. Light reaches the Moon in about 1.3 seconds. To Jupiter, sunlight takes around 43 minutes. To Neptune, over 4 hours. So if the Sun vanished suddenly, though let us agree not to encourage such behaviour, Earth would continue receiving light and gravity information for a short time before noticing. The solar system is large enough that even light cannot cross it instantly. That fact alone can gently rearrange perspective. Now think about travel by spacecraft. The Apollo missions reach the Moon in a matter of days because the Moon is nearby in cosmic terms. Mars missions usually take many months depending on orbital timing and route. Voyages to Jupiter take years. To Pluto, nearly a decade in the case of New Horizons. Even with advanced engineering, crossing our own planetary neighbourhood requires patience. We sometimes speak casually about going to Mars, as if it were a longer train ride. In truth, it is an interplanetary undertaking involving launch windows, fuel constraints, radiation exposure, life support, and many chances for machinery to develop strong opinions. Distance changes difficulty. The planets themselves also reveal scale in another way. Size differences. Earth's diameter is about 12,742 kilometres. Jupiter's is roughly 139,820 kilometres. More than 11 Earths could fit across Jupiter's diameter. Over 1,300 Earths could fit inside Jupiter by volume. The Sun is larger still. Over 1 million Earths could fit inside it by volume. And yet the Sun is considered an ordinary star by galactic standards. Humility arrives reliably in astronomy. Still, planetary size does not equal planetary importance to us. Earth remains home, the only confirmed life-bearing world we know. A peppercorn perhaps, but a precious one. Now let us move beyond Neptune. Neptune orbits at about 30 astronomical units, but the solar system does not end there. The Kuiper belt extends beyond Neptune, containing icy bodies, dwarf planets, and remnants from early formation. Pluto averages around 39 astronomical units from the Sun. Some Kuiper belt objects travel much farther. Then there may be the Oort cloud, a vast spherical reservoir of icy bodies thought to surround the solar system at tremendous distances, perhaps thousands to over 100,000 astronomical units away. If the Oort cloud exists as modelled, the Sun's gravitational influence stretches into a region almost halfway to nearby stars. The edge of home becomes blurry. That is common in science. Boundaries often fade rather than snap. Where does the solar system truly end? At Neptune? At Pluto? At the heliopause, where the solar wind meets interstellar space? At the farthest object still gravitationally tied to the Sun? Reasonable people choose different definitions. The Voyager 1 and Voyager 2 spacecraft have crossed the heliopause into interstellar space, meaning they passed beyond the Sun's protective bubble of solar wind. Yet they are still gravitationally bound to the Sun, and would take tens of thousands of years to approach another star region. Leaving one boundary does not mean leaving all of them. That idea may apply elsewhere in life too. Now imagine standing somewhere beyond the planets and looking inward. The Sun would still dominate. The planets would be tiny points near a bright centre. Earth itself would be invisible without instruments. All of human history would reside on an unresolvable speck, and yet that speck contains languages, oceans, music, grief, medicine, memory, jokes, migrations, kindness, storms, mathematics, and whoever invented warm blankets. Small does not mean trivial. One of the gifts of scale is that it can reduce ego without reducing meaning. Another fascinating consequence of scale is delay. Communication with distant spacecraft takes time because signals move at light speed. Commands sent to Mars can take minutes, to outer planets, hours. There is no instant cosmic conversation. Robotic explorers must often think for themselves within limits, because Earth is too far for quick guidance. Distance encourages autonomy. Even planetary alignments depend on scale. Missions are timed to use gravitational assists, borrowing momentum from planets through carefully planned flybys. Voyager 2 visited multiple giant planets, partly because a rare alignment made such a route efficient. Timing matters when distances are grand. And yet, despite all this vastness, the solar system is still local. Compared with distances between stars, it is a neighbourhood block. The nearest star system beyond the Sun, Alpha Centauri, lies over 4 light-years away. Our planetary region, immense to us, is tiny compared with interstellar gaps. Soon we will go there. But for now, remain with the scale of what already surrounds us. You're on a planet 150 million kilometres from its star. That planet circles once each year through a mostly empty system, extending far beyond visible planets. Light itself needs hours to reach the outskirts. Human machines require years to cross portions of it. And all of this still counts as nearby. There is comfort in learning the size of things. Problems that felt total can become local. Schedules shrink. Annoyances soften. Perspective returns. The kettle that took too long to boil. The email unanswered. The sock whose partner vanished. Still real, perhaps, but now held inside a wider frame. Tonight, somewhere on the 3rd planet from the Sun, you're resting in a small room on a small world inside a very large neighbourhood. That may sound diminishing, but it can also be freeing. You do not need to fill the universe, you only need to be here. Every morning, without ceremony, it returns. Light gathers at the edges of curtains. Walls brighten, shadows retreat. Birds begin negotiations with silence. Streets warm slowly. Windows catch fire for a few moments in gold. We call it sunrise, though by now we know Earth is the one turning. Still, the name remains useful, and perhaps a little too lovely to surrender. Tonight we turn our attention to the object at the centre of our neighbourhood. The star that holds the solar system together, powers Earth's climate, feeds nearly every ecosystem, and has quietly supported every human generation that ever lived. The Sun is our local star. That phrase matters. It is not the star of the universe. It is one star among hundreds of billions in the Milky Way, and likely one among trillions across the observable cosmos. Yet for us, it is singular in importance. Without the Sun, there is no ordinary Earth story. No oceans as we know them. No weather. No forests. No agriculture. No breathable biosphere. No comfortable afternoon naps. No one asking philosophical questions while avoiding chores. The Sun is not background scenery. It is the engine of home. Let us begin with size. The Sun's diameter is about 1.39 million kilometres. More than 109 Earths could fit across it side by side. By volume, around 1.3 million Earths could fit inside, though compression and geometry complicate any attempt to use them as storage containers. Its mass is even more impressive. The Sun contains about 99.8% of all the mass in the solar system. Every planet, moon, asteroid, comet, spacecraft and wandering grain of dust combined make up only a small remainder. This means when we say planets orbit the Sun, we are speaking about gravity shaped by overwhelming imbalance. The Sun dominates because it is heavy. Mass in astronomy is influence. And yet, despite its enormous presence in our lives, the Sun is considered an ordinary star by stellar standards. It is classified as a G-type main sequence star, often called a yellow dwarf, though it appears white in space and only yellowish through Earth's atmosphere. There are stars much larger, hotter, brighter, stranger, shorter-lived, or more dramatic. Some would swallow the inner planets if placed where our Sun sits. Others are dim red dwarfs that sip fuel slowly for trillions of years. The universe contains show-offs. Our Sun is comparatively steady. That steadiness may be one reason life had time to become complicated here. Now, what is the Sun made of? Mostly hydrogen, with a great deal of helium and traces of heavier elements. Roughly speaking, about 3/4 of its mass began as hydrogen, around 1/4 helium, with small amounts of oxygen, carbon, neon, iron and others. So the great golden disk of human imagination is, in physical terms, a giant sphere of hot plasma. Plasma is matter so energized that electrons are separated from nuclei. It is not solid, liquid, or gas in the everyday sense. It is electrically active, fluid-like, and responsive to magnetic fields. The Sun is not burning like wood in a fireplace. It shines through nuclear fusion. Deep in the core, pressures and temperatures are immense. Temperatures there reach around 15 million degrees Celsius. Under such conditions, hydrogen nuclei can overcome their mutual repulsion and fuse into helium. This process releases energy according to one of physics' most famous relationships: mass converted into energy. Tiny amounts of mass become enormous amounts of light and heat. The Sun performs this quietly, continuously, and with excellent punctuality. Every second, the Sun converts around 600 million tons of hydrogen into helium. Of that, several million tons of mass become pure energy. That energy eventually works its way outward and radiates into space. Some of it reaches Earth 8 minutes later. Sunlight you felt today began as events in the solar core long ago. Though the path outward through dense solar material is slow and complex, photons can take thousands to hundreds of thousands of years through countless interactions before finally escaping the surface. Once free, they cross space to Earth in about 8 minutes. The longest commute ends with daylight on your kitchen table. The visible surface of the Sun is called the photosphere. It is around 5,500 degrees Celsius. Above it lie thinner atmospheric layers, the chromosphere and the corona. The corona is especially curious. It is far hotter than the visible surface, reaching millions of degrees, a puzzle connected to magnetic processes not yet perfectly solved. Science occasionally says, this outer part is hotter than the inner visible part, and yes, we're still working on that. Fair enough. The Sun rotates too, though not like a rigid ball. Because it is plasma, different latitudes rotate at different speeds. The equator turns faster than the poles. This differential rotation twists magnetic fields into elaborate shapes. Those magnetic fields drive much of solar activity: sunspots, flares, prominences, and coronal mass ejections. Sunspots are darker, cooler regions linked to intense magnetic fields. They can be larger than Earth, though cooler is relative here. A slightly cooler patch on the Sun remains catastrophically warm by human standards. Solar flares release bursts of radiation. Coronal mass ejections hurl charged particles into space. When these reach Earth, they can disturb our magnetosphere, affect satellites, disrupt communications, strain power grids, and produce beautiful auroras. So when shimmering lights dance across polar skies, part of the story began with solar tantrums. The Sun gives warmth and occasionally paperwork. It follows cycles as well. Roughly every 11 years, solar magnetic activity rises and falls. Sunspot numbers increase, then decrease, then reverse magnetic polarity over a longer 22-year magnetic cycle. Even stars have seasons of mood. Now let us talk about dependence. Nearly all life on Earth runs on solar energy directly or indirectly. Plants capture sunlight through photosynthesis, converting it into chemical energy. Those plants feed ecosystems or feed creatures that feed ecosystems. Fossil fuels are ancient sunlight stored in old biomass. Wind exists largely because uneven solar heating drives atmospheric motion. Many weather systems are sunlight translated through air and water. You're living in a solar economy. Even your own body rhythms respond to light. Circadian systems use daylight to regulate sleep, hormones, alertness, and metabolism. Morning light helps set internal clocks. Evening darkness invites melatonin. Artificial lighting can confuse the arrangement, but the original schedule is solar. The sun reaches into biology. Human culture reflects this deeply. Calendars, harvest festivals, architecture, solstice monuments, prayer times, work days, myths, and symbols all bear traces of solar importance. Ancient civilizations tracked its rising points on the horizon. Farmers watched seasonal light. Builders aligned monuments. People everywhere noticed the star that decides whether fields grow. One need not understand fusion to appreciate dependable dawn, and yet the sun is not eternal. It is about 4.6 billion years old and roughly halfway through its main sequence lifetime. It has enough hydrogen fuel in the core for about another 5 billion years or so. Eventually, the core hydrogen supply will decline. The sun will change. It will swell into a red giant, likely engulfing or scorching the inner planets, shed outer layers, and leave behind a white dwarf remnant. This is not a pressing concern for tomorrow's schedule. It is, however, a reminder that stars have life cycles. Our local star had a birth, has a present maturity, and will have an ending. The atoms in your body heavier than helium were forged in earlier stars that lived and died before the sun formed. In that sense, the sun is not the first chapter, but a later generation. You are warmed by a descendant star using inherited matter. That is a respectable family history. The sun also moves through the galaxy, carrying us all with it. It is not fixed in some central throne room. It orbits the galactic center alongside countless other stars. Our entire solar system follows the sun through the Milky Way, like a small fleet around a flagship. So when you stand in sunlight, you stand in light from a moving star on a moving path through a moving galaxy. The room may feel still, but the architecture of reality remains energetic. There are practical reasons to study the sun intensely. Space weather forecasting matters for satellites, aviation, navigation systems, astronauts, communications, and electrical infrastructure. Telescopes watch the sun continuously. Spacecraft monitor solar wind. Models improve year by year. Civilization has become technologically sensitive to stellar behavior. An earlier farmer worried about drought. A modern engineer may also worry about coronal mass ejections. Different centuries, same star. And despite all our measurements, the sun still works emotionally on people. A warm morning after weeks of cloud, winter light through a window, long summer evenings, the relief of dawn after a difficult night, the comfort of ordinary daylight on ordinary objects. Science explains the mechanism. It does not cancel the feeling. That may be one of the nicest truths in learning. Understanding that the sun is a fusion-powered plasmasphere 150 million kilometers away does not make sunrise less beautiful. If anything, it adds depth. Beauty with structure often lasts longer than beauty alone. Now imagine for a moment seeing Earth from space with the sun in view. A small blue world lit on one side, darkness on the other, rotating through a narrow zone of dawn and dusk. Every city morning, every evening walk, every sleepless hour, every breakfast, every farewell, every child learning shadows, all governed by one star's light meeting one planet's spin. Simple geometry, endless consequence. Once the planets fade into distance and the sun becomes smaller behind us, it might seem reasonable to think its influence simply ends. Light grows weaker. Warmth drops sharply. The bright centre of the solar system becomes another star among many. Surely somewhere out there the sun stops mattering. But stars are not only lanterns, they are also winds. Tonight we travel into one of the least visible yet most important structures surrounding our cosmic home, the heliosphere, the vast bubble carved into interstellar space by the sun itself. You cannot see it with the naked eye. It does not glow in the sky like the moon or rise each morning like daylight. Yet every planet in the solar system lives inside it, including you. The heliosphere is formed by the solar wind, a continuous stream of charged particles flowing outward from the sun in all directions. Mostly electrons and protons, this plasma escapes the sun's outer atmosphere and rushes into space at hundreds of kilometers per second. Our star is constantly shedding material, not dramatically enough to alarm breakfast tables, but steadily enough to shape a region far larger than the planetary system most people imagine. This means the space between planets is not empty in the ordinary sense. It is filled with sunlight, magnetic fields, dust, radiation, and streams of solar particles. Space inside the solar system is an environment, not a blank pause. The solar wind races outward past Mercury, past Venus, past Earth, past Mars, through the asteroid belt beyond Jupiter and Saturn, onward toward the dark outer reaches. As it expands, it carries the sun's magnetic field with it, twisted into a spiral shape by the sun's rotation. This structure is known as the Parker spiral, after physicist Eugene Parker, whose work helped explain solar wind theory. So even the magnetic geometry of our local space has a graceful swirl to it. Now imagine this outward flow meeting the thin gas and particles that exist between stars, the interstellar medium. The solar wind pushes outward. Interstellar material presses inward. Somewhere far from the sun, a boundary forms. That boundary region defines the heliosphere. You can think of it as the sun's personal weather system extending into the galaxy. Not a hard shell, not a clean wall, but a changing frontier where one star's influence meets the broader Milky Way. Earth orbits comfortably deep inside this bubble, protected from much of the harsh galactic radiation beyond. The heliosphere helps deflect or reduce some incoming cosmic rays, energetic particles arriving from supernova remnants and other violent astrophysical sources. So while it sounds abstract, the heliosphere may have practical importance for life. Your peaceful evening benefits partly from invisible plasma dynamics far beyond Neptune. This is a recurring theme in astronomy. The universe does enormous things quietly. The heliosphere has several regions worth knowing. First is the inner solar wind zone, where particles stream outward supersonically from the sun. Farther away lies the termination shock, where the solar wind slows abruptly after encountering resistance from interstellar material. Beyond that is the heliosheath, a turbulent region where slowed solar wind piles up and becomes more chaotic. Then comes the heliopause, the outer boundary where the pressure of solar wind balances against the interstellar medium. Cross that line, and you have entered interstellar space in an important physical sense. This does not mean you have left the sun's gravity entirely. Gravity reaches far. But it means the solar wind no longer dominates local particle conditions. Boundaries in space, as usual, are layered and subtle. The heliosphere is not perfectly spherical either. It is shaped by solar motion through the galaxy, by magnetic fields, by varying particle pressures, and by changing solar activity. Scientists debate details of its form. It may resemble a comet-like tail, or something more rounded and complex, perhaps with twin lobes or croissant-like features depending on the model. Yes, there was a period when serious scientific discussion included whether our solar bubble resembles a croissant. Science remains admirable. Because the sun moves through the Milky Way, the heliosphere is not static. It drifts with us through local interstellar space, carrying planets inside like passengers within a moving magnetic vessel. We are not merely orbiting a star, we are travelling inside its extended atmosphere. This helps explain why "where are we?" always becomes richer than expected. At the scale of daily life, you are in a room. At the planetary scale, on Earth. At the solar scale, orbiting the sun. At a larger scale still, you're inside a star-made bubble gliding through the galaxy. That is a respectable address. Now let us talk about how we learned any of this, since heliospheres are inconveniently hard to photograph from the outside. We have never sent a camera far enough away to turn around and take a neat family portrait. Instead, we infer structure through theory, particle measurements, magnetic field readings, energetic atom imaging, and spacecraft that journeyed outward. Most famous among these are Voyager 1 and Voyager 2, launched in 1977. Originally built to study outer planets, both continued onward for decades after their grand planetary tours. Eventually, each spacecraft crossed the heliopause. Voyager 1 did so first in 2012. Voyager 2 followed in 2018. They did not burst through a dramatic glowing barrier while orchestras swelled. Reality was quieter. Particle counts changed. Magnetic conditions shifted. Data told the story. That is often how frontier science works. Less fireworks, more graphs. Still, those crossings were historic. Human-made objects entered the region between stars carrying instruments and, in the case of the Voyagers, golden records containing sounds and images from Earth. Tiny emissaries from a small world crossed the edge of our star's wind. The heliosphere also changes with the solar cycle. During periods of high solar activity, stronger solar wind and magnetic complexity can alter its shape and shielding properties. During quieter periods, conditions shift again. Home's outer walls breathe. This matters because cosmic rays may influence spacecraft electronics, astronaut safety, and perhaps even atmospheric processes on Earth in subtle ways still studied carefully. The heliosphere acts less like a fortress and more like a dynamic filter. Nothing in nature prefers rigid simplicity for long. There is also something psychologically comforting here. We often imagine space as immediate exposure to infinite harshness. Yet our solar system carries with it a zone of partial shelter, generated by the star that nourishes us. The sun does not only light the house, it extends the porch. Now the heliosphere is large, but not limitless. Beyond it lies the local interstellar medium, a thin region of gas, dust and magnetic fields between stars. Our sun currently moves through a structure called the local interstellar cloud, itself part of a broader local environment. That means even outside the heliosphere, we are not in absolute emptiness. We are in another medium, another neighbourhood, another context. The universe loves nested layers. Inside the heliosphere, planetary magnetospheres create smaller shields. Earth has one. Jupiter has a giant one. So you live inside Earth's magnetosphere, inside the heliosphere, inside the Milky Way, inside larger cosmic structures still to come. Protection within protection, motion within motion. Another subtle point. The heliosphere likely changes over geological time as the sun travels through different interstellar regions. Denser clouds, stronger magnetic environments, or changing solar behaviour may alter its size and shielding. This means Earth's long-term radiation environment may not be perfectly constant over millions of years. Even cosmic weather has climate. If someday humanity spreads outward, understanding the heliosphere will become practical in new ways. Routes for deep space missions, radiation planning, communication systems, and future habitats will all care about particle environments beyond planetary orbits. Today it sounds remote. Tomorrow it may be logistics. For now, though, picture this gently. Far beyond the orbit of Neptune, beyond the Kuiper Belt where icy bodies drift, beyond the familiar planets and well past where sunlight has become dim and thin, the sun's wind slows and mingles with the galaxy. There, an invisible frontier shifts softly in darkness, and deep inside that immense boundary, one small blue planet circles in warmth enough for oceans and sleep. Sometimes we search for meaning in dramatic places, but reality often hides wonder in invisible structures doing steady work. You cannot look up and see the heliosphere tonight, yet it surrounds you all the same. Until now, we have stayed close to home. We began with your room, your coordinates, the ground beneath you, the turning Earth, the moon, the planets, the sun, and the vast heliosphere surrounding our local star. Already the scale has grown far beyond ordinary life. Yet in cosmic terms, we have only walked to the end of the driveway. Tonight we step beyond the solar neighbourhood and into something far grander. We are entering the Milky Way. This is the galaxy that contains our sun, our planets, our sky, and the long history of every human question ever asked under starlight. It is not the whole universe. It is not even the only galaxy nearby, but it is our galactic home, the immense star city in which the solar system occupies one modest address. The word galaxy can sound abstract until you remember what it means. A galaxy is a gravitationally bound system of stars, gas, dust, dark matter, star clusters, nebulae, black holes, and history written in motion. It is structure on a scale so large that individual stars become citizens rather than landmarks, and our galaxy contains hundreds of billions of them. That number can slide past the mind too easily, so let us pause there. Hundreds of billions of stars. Some are larger than the Sun, some smaller, some newborn in dusty nurseries, some ancient and dim, some orbited by planets, some paired in binary systems, some long dead, their outer layers scattered back into space, some perhaps lighting worlds where other beings ask where they are, all of them held together in one vast rotating system. The Milky Way appears in our night sky as a pale band of light stretching across darkness. Ancient people saw it long before telescopes and gave it names rooted in milk, rivers, pathways, smoke, or heavenly roads. The English name Milky Way comes from its soft white appearance. That hazy glow is not cloud. It is the combined light of countless distant stars too numerous and faint to distinguish individually with the naked eye. When you see the Milky Way from a dark place, you are seeing the disk of our own galaxy from inside it. That is an odd and beautiful situation. We are residents trying to understand the shape of our city while standing in one of its suburbs. Imagine trying to map an entire forest while living inside one tree. For centuries, people debated what the Milky Way was. In 1610, Galileo Galilei pointed a telescope toward it and resolved parts of the haze into innumerable stars. The mist became population. Later, astronomers mapped star distributions, studied motions, measured distances, and gradually realized that the Sun is not near the center. We are off to one side in a spiral galaxy with structure, rotation, and a crowded, luminous heart. That discovery changed human perspective profoundly. We were not in the center of the solar system. They're not in the center of the galaxy. They're not in the center of the universe. Science has a gentle habit of relocating our ego. So what does the Milky Way look like? It is a barred spiral galaxy. That means it has a central bar-shaped concentration of stars with spiral arms extending outward. These arms are not rigid solid structures like grooves on a wheel. They are regions of enhanced density, waves of matter where gas compresses and star formation can be more active. Spiral arms are patterns moving through stars and gas, not permanent painted lines. Galaxies, like many things in astronomy, are more fluid than first impressions suggest. The Milky Way's diameter is commonly estimated at around 100,000 light-years, though extended structures and faint outer regions may stretch farther. The disk is relatively thin compared with its width, containing much of the visible stellar population, gas and dust. Above and below the disk lies the galactic halo, a broader region containing old stars, globular clusters, and substantial dark matter. Dark matter, while still mysterious in composition, appears to provide much of the galaxy's mass through its gravitational effects. Without it, observed motions would make less sense than physicists generally tolerate. At the center of the galaxy lies Sagittarius A star, a supermassive black hole with about 4 million times the Sun's mass. Stars orbit it at high speeds. Gas swirls nearby. The galactic center is a dense, energetic environment very unlike our quieter neighborhood. So while your evening may currently involve blankets and calm breathing, the center of your galaxy is conducting itself rather differently. Now let us talk about where the Sun fits into this. Our solar system is located in the galactic disk, far from the central bulge, in a smaller spiral feature often called the Orion Arm or Orion Spur, between the larger Sagittarius and Perseus arms. We are not on the crowded downtown block. We are in a relatively ordinary suburban lane. This position may be fortunate. Regions nearer the galactic centre can be denser, more radiation-rich and more dynamically intense. Our location offers enough heavy elements from prior generations of stars to build rocky planets, while avoiding some harsher environments. Again, not destiny, just circumstance. The stars you see at night belong mostly to the Milky Way. Some are nearby galactic standards, a few light years to tens of light years away. Others are hundreds or thousands of light years distant. Constellations look flat to us, but their stars are spread across different depths, like lanterns scattered through fog. The sky is three-dimensional, disguised as two-dimensional. This can be strangely comforting. Familiar patterns are real enough to guide stories, but not physically grouped the way they appear. As we enter the Milky Way conceptually, we also enter deep time. Stars are born when cold gas clouds collapse under gravity. New stars ignite, shine for millions to billions of years depending on mass, then die in different ways. Some fade gently, some swell into red giants. Massive ones explode as supernovae, enriching space with heavier elements. Those elements later form new stars, planets, oceans, rocks, and living bodies. The calcium in your bones, the iron in your blood, the oxygen you breathe, the carbon in your cells, all were forged in ancient stars. So entering the Milky Way is also entering ancestry. You are made of galactic recycling. Dust in the poetic sense is lovely. Dust in the stellar nucleosynthesis sense is accurate. The galaxy is not silent either. Radio waves, X-rays, gamma rays, magnetic fields, stellar winds, pulsars, nebulae, and collisions all contribute to a dynamic environment invisible to ordinary senses. The calm black sky hides astonishing activity. Astronomy often works by revealing busy things that look quiet. And because light takes time to travel, observing the galaxy means observing history. A star 500 light-years away is seen as it was 500 years ago. A nebula 5,000 light-years away appears as it was when many human civilizations looked quite different than now. When you look outward, you look backward. This applies within our own galaxy long before we reach distant galaxies. Now imagine zooming out beyond the solar system far enough to see the Milky Way from outside. You would see a barred spiral disk glowing with starlight, dust lanes threading through arms, clusters scattered around, faint halo structures, and one tiny star among billions carrying Earth. That star would not be labelled. No marker would announce oceans here, music here, laughter here. One species mildly worried about deadlines here. Yet that tiny unlabelled star is ours. There is tenderness in anonymity. We often think significance requires central placement, but the universe disagrees. Meaning can exist in outskirts. Importance can happen quietly in one modest system far from the galactic core. Our location also means the night sky changes slowly as we orbit the galaxy. Over millions of years, constellations distort. Stars drift. The sun travels through different galactic regions. Nothing overhead is fixed forever. Even familiar heavens are temporary arrangements. Still, on human timescales, the galaxy offers continuity. Night after night, year after year, people have looked upward and seen the Milky Way arching over deserts, mountains, oceans, villages, cities, ships, temples, observatories, campsites, and apartment rooftops. Different languages, same galaxy. That means your address has grown again. Not only Earth, not only the solar system, but the Milky Way. Knowing that we live inside the Milky Way is satisfying in the same way knowing you live in a city is satisfying. It gives context. It tells you the larger place you belong to. But after that first answer comes a second, more detailed question. Yes, but where in the galaxy? If someone says they live in Paris, Tokyo, Nairobi or Sao Paulo, we still do not know whether they are downtown, near a river, in the outskirts, above a bakery, or beside a train line that begins operations with suspicious enthusiasm at dawn. The same is true of galaxies. Tonight we narrow our cosmic address, We move from inside the Milky Way to something more precise. We ask where our Sun, our planets, and therefore you, are located within this enormous rotating system of stars. The short answer is this. We are in the galactic disk, in a minor spiral feature called the Orion Arm, or Orion Spur, roughly halfway to 2/3 of the way from the centre to the outer edge, about 26,000 to 27,000 light-years from the galactic centre. That sentence contains enough wonder to keep us busy for a while. Let us unfold it gently. First, the galactic disk. The Milky Way is not a perfect sphere of stars evenly scattered in all directions. Much of its visible matter lies in a flattened rotating disk, where stars, gas and dust orbit the centre. Spiral arms thread through this disk as density patterns rich in gas and star formation. Our solar system lives within that disk. That means when you look along the plane of the Milky Way on a dark night, you see the crowded lane of our galaxy's stellar traffic. When you look above or below that plane, the star density generally thins. We live inside the busy layer. Second, the spiral feature. Textbooks often list major spiral arms such as Sagittarius, Perseus and Scutum Centaurus. Our Sun does not sit squarely in one of the largest arms. Instead, we appear to occupy a smaller structure between major arms called the Orion Spur, also known as the Local Spur or Orion Cygnus Arm. Think of it as a branch road between larger highways. That modesty suits us. We're not in the dazzling central district or on a giant main arm, crowded with the galaxy's grandest headlines. We are in a quieter side lane with enough stars to be interesting and enough space to be practical. The Orion Spur contains many notable neighbours, including the bright stars of Orion visible from Earth, hence the name. It also includes star-forming regions, clusters, gas clouds, and the wider stellar environment through which our Sun moves. We do not merely observe Orion from afar, we share its neighbourhood. Third, distance from the centre. The galactic centre lies in the direction of the constellation Sagittarius, hidden behind dust when viewed in visible light. There, stars crowd densely around Sagittarius A star, the Milky Way's central supermassive black hole. We are about 26,000 to 27,000 light-years from that centre. That means light leaving the galactic core when early human civilizations were still young would only now be reaching us. It also means we are nowhere near the middle. For a long time, people assumed or hoped humanity occupied central positions in cosmic structures. Earth seemed central once, then the Sun, then perhaps the galaxy. Science steadily revised those hopes with admirable consistency. We are off-centre, and that may be beneficial. Regions near galactic centres tend to be denser, more gravitationally busy, and more exposed to energetic phenomena. Stars crowd closer together. Supernova rates may be higher. Radiation environments can be harsher. Disturbances to planetary systems may be more common. Farther out, heavy elements may become scarcer in some regions, reducing material available for rocky planet formation. Our location may sit in a useful middle range, not too crowded, not too barren. Astronomers sometimes discuss a galactic habitable zone, the idea that certain regions of galaxies may be more favourable for long-term complex life. The concept is debated and refined, but it highlights an interesting possibility. Not every galactic address is equally gentle. Once again, Earth seems to occupy practical real estate. Now let us talk vertically. The Sun does not lie exactly in the midplane of the galaxy. It oscillates above and below the galactic plane over long timescales, moving tens of light-years in a slow bobbing motion as it orbits. So even our local galactic address has seasonal altitude, if one is patient enough to measure seasons in millions of years. The solar system is a commuter. How do we know where we are? Unlike city addresses, there are no galactic street signs reading "You are now entering Orion Spur." Astronomers determine our position through many methods, measuring distances to stars and star-forming regions, mapping radio emissions, tracking stellar motions, studying gas clouds, using parallax measurements and constructing models from vast data sets. Modern missions like Gaia have transformed this effort by precisely measuring positions and motions of more than 1 billion stars. That is map-making on an extravagant scale. From these data, we infer the Milky Way's structure and our place within it more clearly than ever before, though some details remain under active study. Spiral galaxies viewed from inside are tricky to map, much like understanding a forest while standing among trees. Still, the picture is sharpened beautifully. What is our immediate stellar neighbourhood like? Within a few dozen light-years of the Sun are many nearby stars, most of them faint red dwarfs rather than brilliant beacons. The nearest star system beyond our own is Alpha Centauri, about 4.37 light-years away. Nearby also are Barnard's star, Sirius, Procyon, and others. This means our galactic district is populated but not crowded. Stars are separated by vast distances. Even in our neighbourhood, the space between systems is immense. So if the Milky Way is a city, it is one where houses may be separated by trillions of kilometres, and where visiting neighbours requires propulsion, patience, and excellent planning. There is also the local bubble, a region of relatively thin hot gas surrounding the solar system, likely shaped by ancient supernovae. We will visit that more fully later, but it reminds us that even empty local space has structure and history. Our address is layered. Orion Spur, local bubble, galactic disk, 26,000 light-years from centre, orbiting with billions of stars, and all of it in motion. The Sun travels around the galactic centre at roughly 828,000 kilometres per hour. One full orbit takes about 225 to 250 million years. Since dinosaurs walked Earth, the solar system has moved significantly through the galaxy. Since humans appeared, only a tiny fraction of one galactic year has passed. Human history occupies barely a moment of our orbital route. That can feel humbling, but it can also feel grounding. Civilizations rise and fall while the galaxy turns steadily on. Now imagine if aliens requested our address. You might say, third planet of a G-type star called the Sun, located in the Orion Spur of the Milky Way, around 26,000 light-years from the galactic centre. This is a stronger answer than near the big bright thing, though perhaps less conversational. There is something emotionally useful in knowing we are not central. Central positions are overrated. They tend to be crowded, noisy, and difficult to park in. The outskirts and middle districts often allow calmer development. Our galactic suburb may have offered billions of years of relative stability, enough for oceans to persist, life to evolve, intelligence to emerge, and someone to listen quietly while wrapped in a blanket. That is not a bad neighbourhood record. The stars you see in familiar constellations are part of this same broader address. Some belong to our spur, some to nearby structures, all moving in their own orbits. Constellations are local patterns imposed on deeper three-dimensional reality. The galaxy is less a wall of stars than a layered landscape. When you look toward the dense Milky Way band, you look through long lanes of stellar population, gas and dust within the disk. When you look away from it, you look toward thinner directions. Night sky brightness itself reflects your location inside a disk-shaped system. You can sense your galactic placement with naked eyes under dark skies. No app required. And yet, most nights in cities, artificial lights wash that structure away. Many people live their whole lives without clearly seeing the Milky Way overhead. That is a modern loss, though understandable. We built brightness for comfort and accidentally dimmed perspective. Still, the galaxy remains above every rooftop, whether seen or not. If you could leave Earth, pass the planets, move beyond the heliosphere, travel outward through interstellar darkness, and then turn around from a safe and patient distance, you would see something extraordinary. Not a random cloud of stars, not a shapeless scatter of lights. You would see a galaxy with structure. The Milky Way, our home galaxy, has form, scale, motion, and architecture on a level so large that ordinary intuition needs a quiet moment to catch up. Tonight, we step back far enough to appreciate what kind of place we actually live in. The Milky Way is commonly classified as a barred spiral galaxy. That means it has a bright central region crossed by an elongated bar of stars, with spiral arms extending outward through a flattened disk. If galaxies were neighbourhoods, ours would not be a tidy circle or a simple wheel. It would be more like a rotating city with sweeping luminous avenues, dusty side streets, a crowded downtown core, and long curving suburbs made of stars. The phrase barred spiral may sound technical, but the picture is elegant. At the centre lies a dense bulge of stars. Running through that bulge is the bar, an elongated stellar structure thought to help channel gas inward and influence spiral patterns farther out. From the ends of the bar emerge major spiral arms, where gas clouds, young stars and star formation regions are often concentrated. These arms are not solid permanent ridges, they are more like traffic patterns. Stars move in and out of them over time. Gas compresses there, new stars ignite, bright clusters form, and the galaxy's visual spiral shape persists through dynamic processes rather than rigid construction. Even galaxies prefer flow over stiffness. Now let us consider size. The visible stellar disk of the Milky Way is often estimated at roughly 100,000 light-years across, though depending on how one defines faint outer regions, streams, and extended structures, the full span may be larger. A light-year is the distance light travels in 1 year, about 9.46 trillion kilometres. So when we say 100,000 light-years, we are already beyond the range of a language built for grocery lists and calendars. If a beam of light began crossing the Milky Way when early modern humans were emerging as a species, it would only now be nearing the other side. That is one way to feel scale settle in. The disk is comparatively thin relative to its width. Estimates vary, but the thin stellar disk is only a few thousand light-years thick in many regions, with thicker components extending more broadly. Think of a vast cosmic pancake. If pancakes contained stars, dust, black holes, radio waves, and occasional philosophical consequences. The Sun resides within this disk, not near the centre, but out in the Orion spur as we discussed. From inside the disk, we look along crowded star lanes when viewing the Milky Way band in the night sky. That glowing band is edge-on perspective. You're seeing home from within. Now imagine trying to map a city while standing in one alley with no aerial view. That was the challenge astronomers faced for centuries. Dust clouds in the galactic plane obscure visible light, hiding large portions of the inner galaxy from direct optical view. We could see stars. We could not easily see the whole arrangement. So scientists turned to radio waves, infrared observations, stellar motions, distance measurements, and later space telescopes. These wavelengths can peer through dust more effectively. Bit by bit, the map improved. Astronomy often advances by learning to look in new colours. The central bulge of the Milky Way contains older stars packed much more densely than our local region. It is thick, bright, and dynamically busy. At the very centre sits Sagittarius A star, a supermassive black hole with around 4 million solar masses. Stars near it orbit rapidly under strong gravity. Gas heats, moves, and sometimes falls inward. The central environment is energetic in ways your living room admirably avoids. Then there are the spiral arms. Different models identify varying numbers and exact boundaries, but major named arms include Scutum Centaurus, Perseus, Sagittarius and others, with smaller spurs and branches such as our Orion spur. These names can sound like subway lines designed by mythologists, yet they help us orient ourselves in a star system too large for casual landmarks. Spiral arms are important because they often host molecular clouds and star formation. Massive young blue stars illuminate surrounding gas, nebulae glow, stellar nurseries operate, short-lived brilliant stars make arms stand out. Where stars are born, galaxies sparkle. The Milky Way also contains open clusters, groups of younger stars born together, and globular clusters, dense spherical collections of ancient stars orbiting in the halo. Some globular clusters are nearly as old as the galaxy itself. Imagine stellar retirement communities circling far above the disk for billions of years. Now we reach something even larger than the visible disk, the halo. Surrounding the Milky Way is a more diffuse spherical halo containing sparse stars, globular clusters, streams from cannibalized smaller galaxies, and a dominant component of dark matter. Dark matter does not emit light as far as we know, but its gravity strongly affects galactic rotation and structure. Stars in outer regions move faster than visible matter alone would predict. The unseen mass appears substantial. So much of our galaxy's total mass is invisible. This is either unsettling or thrilling, depending on temperament. The Milky Way has grown over time by mergers and accretion. Smaller galaxies have been absorbed, stretched into stellar streams, and incorporated into the larger system. Our galaxy, like many others, was assembled through history rather than appearing fully formed. Galaxies have biographies. Some of those past encounters are still visible as tidal streams arcing through the halo. The Sagittarius dwarf spheroidal galaxy, for example, is being disrupted and gradually absorbed. Even giant star cities expand by annexing suburbs. How many stars are in the Milky Way? Estimates commonly range from 100 billion to perhaps 400 billion or more, depending on assumptions and methods. The exact number is difficult because counting stars in a dusty, structured galaxy from the inside is inconveniently complex. Still, hundreds of billions is safely accurate enough to humble anyone, and planets. Given what exoplanet surveys have shown, planets are likely common. Many stars probably host worlds. Some host several. Some may host dozens of smaller bodies. Multiply that across hundreds of billions of stars, and the number of planets becomes astonishing. Our galaxy may contain more worlds than human imagination can comfortably furnish. The Milky Way is also rotating. Stars orbit the galactic center at different speeds depending on location, mass distribution, and dynamics. The Sun takes roughly 225 to 250 million years to complete one orbit. That means since the time of the dinosaurs, the solar system has travelled around part of the galaxy, but not many full circuits. Human civilization, by contrast, has existed for only a blink of one galactic year. This is not depressing, it is clarifying. We often experience life through deadlines, calendars, quarters, semesters, anniversaries, and mildly threatening reminder notifications. Galactic time quietly suggests another scale exists. There is also beauty in the Milky Way's appearance from Earth. Under dark skies, the band can show knots, dust lanes, bright star clouds, and varying texture. The eye sees structure if given darkness enough to notice. Modern light pollution has hidden this from many people. Entire generations grow up beneath skies where the galaxy is present but unseen. The stars did not leave. We brightened the foreground. Still, in rural deserts, mountains, open seas, and remote landscapes, the Milky Way remains one of nature's most persuasive sights. It reminds viewers instantly that they are inside something vast. And that is the key emotional truth here. The Milky Way is not above you like wallpaper. It surrounds you. Every direction you look points somewhere into it or through it. The stars nearest overhead, the dust beyond them, the distant bulge hidden behind clouds of gas, the halo beyond the disk, all part of the same galaxy. You're not looking at home from outside. You're living within it. Even emptier-looking regions between bright stars are still within the galactic environment, shaped by its gravity, history, and material. There is no outside sky visible from Earth in the ordinary sense. Every naked-eye star you commonly notice belongs to the Milky Way, with a few rare exceptions like Andromeda Galaxy under dark skies. One more lovely detail: because we live inside the disk and not near the centre, our skies are not overwhelmed by dense central brightness. Our position allows dark nights, stable conditions, and a clear enough environment for astronomy to arise. We are placed well enough to notice. That may be one of the most fortunate addresses of all. When we think about orbits, most of us picture the familiar ones first. The Moon around Earth, Earth around the Sun, perhaps satellites circling overhead with quiet efficiency. These motions feel understandable because they fit within human timescales. A month for the Moon, a year for Earth, hours for some spacecraft. We can watch them on calendars, predict them easily, and build routines around them. But there is another orbit underway right now, one so vast and slow that it slips entirely beneath ordinary awareness. The Sun, carrying Earth and everything on it, is orbiting the centre of the Milky Way. You are part of that journey this very moment. Tonight, while you rest in one room on one turning planet, the entire solar system is sweeping through the galaxy at remarkable speed, tracing a path around a centre we cannot see directly with our eyes from most places on Earth. This is one of astronomy's favourite habits, to reveal that calm things are moving magnificently. Let us begin with speed. The Sun travels around the galactic centre at roughly 220 kilometers per second, often approximated in everyday units as around 800,000 kilometers per hour or more depending on the model used. Numbers vary slightly with improved measurements, but the broad picture is clear. We are moving fast, faster than aircraft, faster than bullets, faster than weather systems, faster than most metaphors deserve. And yet, just as with Earth's rotation and orbit around the Sun, you do not feel this movement because everything nearby shares it. The planets, moons, asteroids, comets, spacecraft, your bed, your tea mug, your socks, all travelling together in one gravitational convoy. Shared motion feels like stillness. Now let us consider distance. The Sun is about 26,000 to 27,000 light-years from the galactic centre. That centre lies in the direction of the constellation Sagittarius, hidden behind thick clouds of interstellar dust in visible light. Infrared and radio observations reveal more of the region, including Sagittarius A star, the supermassive black hole anchoring the core. So our orbit is not a neat little circle around an empty point. It is a grand path around a dense dynamic centre, containing stars, gas, dust, and a black hole millions of times the Sun's mass. How long does one orbit take? About 225 to 250 million years. This is sometimes called a cosmic year or galactic year. That timescale is so large that it asks the mind to stretch carefully. If the Sun completed one orbit when the earliest dinosaurs were beginning to appear, it would only now be returning to roughly comparable galactic longitudes. Since the extinction of the dinosaurs about 66 million years ago, the solar system has travelled only a fraction of one galactic lap. Since the first humans appeared, only a tiny fraction. Since written history began, an almost invisible sliver. Since you started listening tonight, enough distance to be measurable in kilometres, but still only a whisper of the whole route. Human history occupies a small bookmark in a very long orbital book. This can feel humbling, but it can also feel strangely soothing. So much of daily stress is built around clocks, deadlines, seasons, years. Galactic motion introduces a scale on which even centuries are brief weather. Now, is the Sun's path a perfect circle? Not exactly. Like many orbits in nature, it is more complex. The Sun moves through the galactic gravitational field in a path influenced by the distribution of mass in the Milky Way. It orbits the centre, but also oscillates slightly inward and outward in radius over long timescales, and bobs above and below the galactic plane. So the solar system is not simply running laps, it is weaving. Imagine a horse on a carousel that also moves up and down while the platform subtly shifts. Then enlarge the system to 100,000 light-years and remove the horse. You're now only slightly closer to the right idea. The bobbing motion above and below the galactic plane may have a period of tens of millions of years. Our Sun passes through the denser midplane region periodically, then rises above or below it again. This has inspired many speculative ideas over the years, some stronger than others, about links to climate, impacts, or biological history. Science remains cautious where evidence is uncertain, but the motion itself is real. We are gentle vertical commuters. How do astronomers know any of this? By measuring motions of stars, mapping gas clouds, studying Doppler shifts, calculating mass distributions, observing stellar positions with missions like Gaia, and building dynamic models of the galaxy. Stars become data points become maps become motion. From Earth, we cannot rise above the Milky Way and film the orbit directly like a drone over a racetrack. We infer the pattern from careful observation inside the system. Again, we are mapping the city while living in it. Now let us think about what the Sun has passed during previous galactic travel. During one orbit, spiral arms may move relative to stars. Nearby stellar neighbourhoods change. Molecular clouds appear and recede. Star clusters disperse. Supernovae occur. Constellations completely rearrange. When the Sun last occupied some similar orbital region hundreds of millions of years ago, Earth had no humans, no cities, no music streaming subscriptions, no bicycles, no bedtime science videos. Life was different. Continents were different. The galaxy, too, was different in details. By the time the Sun completes another full orbit from now, Earth's surface, climate, biology, and perhaps even whether humans remain recognizable, would likely be transformed beyond easy prediction. Galactic years are long enough to make certainty shy. There is another important point here. The Sun is not racing alone. Many nearby stars orbit in broadly similar directions around the galactic centre, though with their own speeds, inclinations, and histories. Some stars overtake others gradually, some drift away. New neighbours appear over millions of years. The local stellar neighbourhood is not permanent. Your cosmic street slowly changes residents. Even the nearest star system today, Alpha Centauri, will not always hold that title forever. Stellar motions rearrange proximity over long spans. Nothing in the galaxy remains socially static. Now let us address the centre itself. The galactic centre is about where all this mass effectively draws us inward, but not in the simple sense of water down a drain. Orbits persist because sideways motion balances inward gravitational pull. The Sun is continually falling toward the centre while continually missing it, just as Earth falls toward the Sun while orbiting. This elegant failure to fall straight in is the basis of many stable systems. Gravity is not always about collapse, often it's about curves, and at the centre, Sagittarius A star exerts strong local influence, but the entire central mass distribution of stars, gas, dark matter, and the bulge contributes to the Sun's orbit. We do not orbit only the black hole, we orbit the galaxy's combined gravitational architecture. That distinction matters, and it also saves us from oversimplified documentaries narrated with too much enthusiasm. Now imagine watching Earth from outside the solar system. You would see a tiny planet orbiting the Sun yearly, then zoom farther out. The Sun itself drifts among stars. Zoom farther still. It traces a huge arc around the Milky Way centre, motion within motion within motion. This layered structure is one reason the question "where are we exactly?" keeps expanding. Every stable answer reveals a larger movement, yet none of this should make you feel lost, quite the opposite. We often think location means standing still at a point. But the universe suggests another model. To belong somewhere may mean moving coherently within something larger. Earth belongs to the solar system by orbiting the Sun. The solar system belongs to the galaxy by orbiting its centre. You belong to Earth by travelling with it. Stillness is not the only form of home. There is also companionship in shared trajectory. Tonight, billions of people are riding this galactic arc together, mostly unaware. Some are asleep, some are working, some are worried, some are celebrating, some are watching stars, some are listening now, all aboard one world, around one star, around one galactic centre. That is a rather grand kind of togetherness. If daily life has felt narrow lately, it may help to remember that your current concerns exist inside a voyage lasting hundreds of millions of years. This does not erase real problems, but perspective can soften their sharpest edges. The unanswered message, the awkward meeting, the mysteriously vanished sock, still present perhaps, but now framed by a galaxy. When we look up at the night sky, the stars can seem evenly scattered and infinitely distant, like decorative lights placed on a dark ceiling. Some are brighter, some dimmer, some arranged into familiar patterns, but they often appear as a flat display rather than a true landscape. That impression is understandable. It is also wrong in one of the most interesting ways possible. The stars above you are not pinned to a surface. They are spread through three-dimensional space at vastly different distances. Some are relatively nearby, cosmic next-door neighbours in galactic terms. Others are far beyond them. Brightness can reflect closeness, true luminosity, or a mixture of both. Familiar constellations are perspective drawings made from objects separated by light years. Tonight we stay in our local district of the Milky Way and meet the nearby stars, the suns sharing our region of the galaxy. These are the neighbours in the night. Let us begin with the nearest one beyond our own sun. That honour belongs to the Alpha Centauri system, about 4.37 light-years away. It is not a single star, but a multiple star system. Two sun-like stars, Alpha Centauri A and Alpha Centauri B, orbit one another, while a smaller red dwarf companion, Proxima Centauri, lies gravitationally associated with them. Proxima Centauri is the nearest known star to the Sun. That means the closest neighbouring sun is not one of the bright stars many people notice first, but a faint red dwarf invisible to the naked eye from Earth. The universe has little interest in rewarding assumptions. Red dwarfs are especially common. Small, cool, dim compared with stars like the Sun, they may be the most numerous stellar type in the galaxy. Many of our closest stellar neighbours are red dwarfs rather than blazing giants. If stars formed a town council, the quiet practical members would likely dominate. Proxima Centauri is especially famous because it hosts at least one known planet, Proxima Centauri b, located in a region where liquid water might be possible under some conditions. Whether it is hospitable in practice is another matter. Red dwarfs can be active stars, producing flares that complicate life's comfort. Even nearby real estate has caveats. The next notable neighbour is Barnard's star, around 6 light-years away. It is another red dwarf, famous for having one of the largest known proper motions across our sky. Proper motion means apparent movement against background stars over time. Given enough years, stars visibly drift. The sky feels permanent because human lifetimes are short. Extend the timeline and constellations loosen, shift, and eventually become unrecognisable. Then there is Sirius, often the brightest star in the night sky as seen from Earth. It lies about 8.6 light-years away, and is actually a binary system. Sirius A, a bright main-sequence star, and Sirius B, a white dwarf, the dense remnant of a once larger star. A bright jewel in the sky turns out to be a paired system, with a stellar corpse in attendance. Astronomy rarely settles for simple versions. Procyon, about 11.5 light-years away, is another nearby binary system with a white dwarf companion. Epsilon Eridani, around 10.5 light-years away, is a younger sun-like star with evidence of planets and debris. Tau Ceti, around 12 light-years distant, is often discussed as a nearby sun-like candidate system. Already we see a pattern. Nearby space is not empty. It contains stars of many kinds, planets, remnants, binaries and systems with stories of their own. Still, the distances remain immense. If the Sun were reduced to the size of a tennis ball, the nearest neighbouring star on that scale might be hundreds of kilometres away. Space between stars is mostly emptiness. The galaxy is populous but spacious. This is worth remembering whenever science fiction shows star systems parked conveniently beside one another like shops on a high street. Reality is less convenient and more majestic. Now let us talk about brightness. Some stars appear bright because they are near, others because they are intrinsically luminous. Sirius is both fairly near and genuinely bright. Meanwhile, some nearby red dwarfs are so dim that you cannot see them without telescopes despite their closeness. Distance and power combine to shape what your eyes receive. This is why the sky can mislead us gently. A bright star may be farther than a dim one. A familiar point may be a giant. A tiny-looking light may host planets. The universe does not label anything. Many nearby stars exist in binary or multiple systems. In fact, a large fraction of stars are not solitary like the Sun. They orbit partners. Some pairs are wide and leisurely, others are close and fast. Some systems contain 3 or more stars in intricate dances. So our own single-star arrangement may be less common than intuition suggests. Planets in multiple star systems are possible too. Nature is more flexible than many screenwriters. How do we know the distances to nearby stars? One of the most elegant methods is stellar parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against more distant background stars. By measuring that tiny annual wobble, astronomers can calculate distance geometrically. This means Earth's orbit becomes a measuring tool. Our yearly path around the Sun is part of the ruler by which nearby space is mapped. Modern missions like Gaia have measured parallaxes for enormous numbers of stars with extraordinary precision, refining our local map dramatically. We now know our neighbourhood better than any previous generation could have imagined, and yet emotionally the stars remain mysterious enough to matter. Consider that every nearby star has its own history. Some formed before the Sun, some after. Some may have rocky planets, some may have icy outer worlds, some may have asteroid belts, comets, magnetic storms, auroras, seasons, or silent barren surfaces circling them in darkness. We do not yet know which worlds, if any, host life nearby. That question remains open, patient, and powerful. The stars nearest us also move relative to the Sun. Over tens of thousands of years, different stars become nearer or farther. Gliese 710 is expected to pass comparatively close in the distant future, perhaps perturbing outer comet reservoirs. Cosmic neighbourhoods change residents. The nearest star today is not guaranteed to remain so forever. This moving neighbourhood has likely influenced the outer solar system at times. Passing stars can disturb distant comet clouds, altering trajectories and perhaps sending some inward over long spans. Even at great distances, stars can be gravitationally social. Nothing exists entirely alone. Now think about what nearby stars meant to earlier humans. Before electricity softened the sky, these lights were practical companions. They marked seasons, directions, navigation routes, planting times, weather traditions, and stories. Sirius was crucial in ancient Egyptian calendrical life through its heliacal rising. Sailors used stellar positions for navigation across oceans. Communities wove identity into constellations and bright seasonal stars. Our neighbours were once clocks, maps, and myths. They still are if we choose to look. There is another comfort hidden here. The nearest stars are not impossibly remote in the scale of the galaxy. Far, yes. Extremely far by current travel methods. But they are local enough that human-made probes moving much faster than ours today could one day reach them within practical lifetimes or generations. Interstellar travel remains difficult but not forbidden by distance alone. The front gate of the galaxy is nearby. Of course, nearby in astronomy can be cheeky. Proxima Centauri is over 40 trillion kilometers away. If you drove there at motorway speed and never stopped, your commitment would become historically notable. Still, compared with the galaxy's full width, it is next door. Tonight, when you look at the stars, many of the points you notice are not anonymous decorations but neighbouring suns in our district of the Milky Way. Some have names we know, some have planets we're still discovering. Some shine brightly because they are powerful, others because they are close. Some are multiple stars in quiet partnership, and somewhere among them, our sun is simply another local light. That perspective can be calming. We're not isolated at the edge of emptiness. We are part of a community of stars spread widely, yes, but real and surrounding. When most people imagine the space between stars, they picture emptiness. A dark vacuum, nothing to speak of. Vast stretches of black where absolutely nothing happens until you arrive at the next star. That picture is understandable. It is also incomplete. The regions between stars are thinly populated compared with planets or stellar surfaces, yes, but they are not nothing. Interstellar space contains gas, dust, magnetic fields, radiation, shock waves, drifting particles, chemistry, and the long after effects of stellar life and death. It is a medium, not a blank. Tonight, we move into our local interstellar neighbourhood and explore one of the most intriguing features surrounding our solar system, the local bubble. You are resting on Earth, orbiting the Sun, travelling through the Milky Way, and currently drifting through a cavity in the interstellar medium likely carved by ancient explosions. Which is a splendidly dramatic sentence for something affecting your evening so quietly. Let us begin with the interstellar medium itself. Between stars lies material spread very thinly, mostly hydrogen gas, some helium, traces of heavier elements, dust grains, cosmic rays, and magnetic fields. In dense clouds, this matter can gather enough to form future stars. In more diffuse regions, it remains sparse and hot. Compared with Earth's atmosphere, interstellar gas is astonishingly tenuous. A laboratory vacuum on Earth can be denser than many parts of space between stars, so yes, it is extremely empty by human standards, but not empty enough to ignore. Over galactic timescales, even thin material matters. It forms stars, absorbs light, carries shock fronts, and preserves evidence of past events. Now to the local bubble. The solar system appears to reside inside a region of relatively low density, high-temperature gas spanning perhaps hundreds of light-years across. This cavity is called the local bubble. Imagine a large irregular chamber in the galactic medium where the gas is thinner than surrounding regions. How did it form? The leading explanation is that multiple supernova explosions, likely from massive stars in nearby stellar groups millions of years ago, blasted surrounding material outward. Shock waves heated gas, cleared denser matter, and left behind a hot bubble-like cavity. In simpler terms, our local space may have been remodeled by dead stars. The cosmos has dramatic renovation methods. These supernovae would have occurred long before humans existed. Their shock waves expanded across space, sculpting the medium between stars. Over time, the Sun drifted into or through this resulting region. So tonight, while you listen peacefully, you're inside a structure probably shaped by ancient stellar explosions. Science is generous with perspective. The local bubble is not a perfect sphere. It is irregular, complex, and connected to neighbouring cavities and tunnels of lower density gas. Mapping it resembles reconstructing foggy architecture from sparse measurements. Astronomers infer its shape using starlight absorption, gas observations, dust mapping, and modern three-dimensional reconstructions. By studying how light from stars is dimmed or altered, scientists can estimate where denser clouds and emptier regions lie. Again, astronomy often learns by noticing what light loses on the journey. Inside the local bubble, gas is hotter than one might expect, perhaps around 1,000,000 degrees in some models, though so thin that it would not feel hot in the ordinary sense because there are too few particles to transfer much heat. This is one of space physics' favourite tricks. Very hot does not always mean fiery. Very empty does not always mean nothing. The Sun is currently embedded within an even smaller feature inside this environment called the local interstellar cloud, sometimes nicknamed the local fluff. This is a relatively denser patch of gas and dust the solar system is moving through. Yes, serious astronomy occasionally names things with unexpected softness, so our full local address includes nested layers: Earth, solar system, heliosphere, local interstellar cloud, local bubble, Milky Way. The universe loves layers. Now let us connect this to the heliosphere we discussed earlier. The heliosphere is the bubble made by the solar wind. It pushes outward against the surrounding interstellar medium. The size and shape of the heliosphere depend partly on what the Sun is moving through. If surrounding interstellar gas were denser, the heliosphere could be compressed. If thinner, it could expand. Different galactic neighbourhoods may subtly alter our star's protective bubble. That means the Sun carries its own local shield, but the shield responds to external weather. Even stars live in environments. Why does this matter? Because the heliosphere helps moderate incoming cosmic rays. Changes in surrounding interstellar conditions could influence radiation reaching the inner solar system. Over geological timescales, such shifts might affect atmospheres, climate chemistry, or biological mutation rates in subtle ways still studied carefully. Nothing here is simple enough for one-sentence certainty, but the principle is clear. Where the solar system travels through the galaxy can matter. Now imagine the local bubble visually. Not a bright soap bubble floating in darkness. Rather, an immense region hundreds of light years wide where surrounding denser gas has been pushed outward, leaving a cavity threaded with hot plasma and structured edges where cooler, denser clouds gather. The Sun is somewhere within this chamber, not at the centre, continuing its orbit around the galaxy. We are cosmic tenants in an old blast zone. There are neighbouring star-forming regions near the bubble's boundaries. Dense molecular clouds at edges may have been compressed by ancient shock fronts, perhaps helping trigger later starbirth. In this way, one generation of stars may have died violently and encouraged the next generation to form. Death-seeding creation is common in astronomy. Heavy elements forged in stars spread outward. Shock waves compress clouds. New stars ignite. Planets form. Eventually, perhaps, life notices. The local bubble may be part of that broader cycle. Our nearby stellar associations, such as groups of young stars in the Scorpius-Centaurus region, are often discussed in connection with supernova history that could have shaped local space. Massive stars live quickly and die explosively, making them efficient architects of interstellar cavities. Short lives, large consequences. There is evidence that one or more supernovae may have occurred relatively near the solar system in geological history, perhaps leaving traces in ocean sediments through isotopes like iron-60. These findings suggest that nearby stellar explosions are not purely theoretical features of distant ages. The galaxy leaves signatures in stone and seabed. Fortunately, nearby in astronomy often still means many light years away. Distance is sufficient to preserve Earth from catastrophic effects while allowing measurable traces. Again, context matters. Interstellar space also contains dust grains, tiny solid particles of carbonaceous or silicate material. These grains help block visible light, redden distant stars, and participate in chemistry. Molecules can form on dust surfaces. Clouds rich in dust and gas become nurseries for future stars and planets. The same kind of raw ingredients that once formed the Sun still drift between stars today. Future worlds are suspended in the dark, and the solar system is moving through all of this. The Sun travels around the galactic centre, carrying us through changing local conditions over millions of years. Different clouds, different densities, different magnetic environments may come and go. Our galactic weather changes slowly. This can be comforting in a strange way. We often imagine home as fixed and external space as distant. But home itself is travelling through a living medium shaped by long history. You're not parked in a static universe. You're sailing through it. Now let us scale emotionally rather than physically. Daily life can feel crowded with immediate details, messages, chores, delays, plans, worries, the mysterious migration of one sock from every pair. Yet beyond the roof tonight lies a solar system inside a star-made bubble, inside a cavity carved by ancient supernovae, inside a galaxy full of similar stories. Perspective does not erase ordinary life. but it gives it room to breathe. The local bubble also reminds us that emptiness can have structure. Silence can hold history. Spaces between obvious things are often full of processes we simply do not notice. That is true in astronomy, and sometimes elsewhere. When you look at the night sky, the darkness between stars is not meaningless blankness. It is medium, memory, chemistry, radiation, motion, and the future birthplace of other suns. Darkness is often busy. For most of this journey, the Milky Way has felt enormous, and fairly so. It contains hundreds of billions of stars, stretches across roughly 100,000 light-years or more, and has enough structure, dust, history, and gravitational complexity to keep astronomers pleasantly occupied for generations. From Earth, the Milky Way can feel like the whole sky. From within our solar system, it feels unimaginably vast. Yet tonight we widen the frame again, because even the Milky Way has neighbours. Our galaxy is not drifting alone through empty darkness. It belongs to a small gravitational community of galaxies known as the local group. This is the next level of our cosmic address, the galactic neighbourhood in which the Milky Way is one resident among several dozen known members. The name is modest, the scale is not. The local group spans roughly 10 million light-years across, depending on how boundaries are defined and which outlying members are included. Within that region, gravity links galaxies in a loose but meaningful association. If the Milky Way is a city, the local group is the county. If the Milky Way is a forest, the local group is the valley containing several forests. If the Milky Way is already overwhelming enough, I understand completely. Let us begin with the two largest members. The first is our own Milky Way. The second is the Andromeda Galaxy, often catalogued as M31. It is the nearest large spiral galaxy to us and lies about 2.5 million light-years away. That means the light reaching Earth from Andromeda tonight began travelling long before humans existed in modern form. While that light crossed intergalactic space, ice ages came and went, civilizations rose and fell, languages formed, oceans shifted coastlines, and countless generations lived ordinary lives. Light is patient. The Andromeda Galaxy is somewhat larger than the Milky Way in visible extent, and contains perhaps 1 trillion stars, though estimates vary. It is another grand spiral system, luminous and majestic, and under dark skies it can be seen with the naked eye as a faint smudge. A smudge containing perhaps 1 trillion suns. The universe is fond of understatement. The third largest major member of the local group is the Triangulum Galaxy, also known as M33. Smaller than Andromeda and the Milky Way, it is still a substantial spiral galaxy in its own right. Then come many smaller galaxies. These include dwarf spheroidal galaxies, dwarf irregular galaxies, satellite galaxies orbiting larger members, and systems in various stages of interaction. Some are rich in gas and star formation, others are dim, diffuse, and ancient. The local group is not a club of giants only, it is full of smaller companions. The Milky Way itself has several known satellite galaxies, including the Large Magellanic Cloud and Small Magellanic Cloud, visible from southern skies, along with numerous dwarf galaxies such as the Sagittarius dwarf spheroidal galaxy. The Andromeda Galaxy has its own satellites too. Galaxies, like stars, often gather company. This is an important shift in perspective. We sometimes imagine galaxies as isolated islands. Many are not. Gravity links them into groups, clusters, and larger structures. They interact, exchange material, distort one another, merge, and evolve through companionship as much as solitude. Even galaxies have social lives. How are these members held together? Through gravity. The combined mass of the local group, much of it in dark matter, binds the galaxies into a shared dynamical system. Members move relative to one another, often orbiting larger galaxies or drifting through the common gravitational field. Dark matter, again, appears crucial. visible stars and gas alone do not explain observed motion sufficiently. Much of the local group's mass seems unseen. The universe continues to keep substantial things in shadow. Now let us talk about perhaps the most famous future event in our neighbourhood. The Andromeda Galaxy and the Milky Way are moving toward one another and are expected to interact and eventually merge billions of years from now. This is often described dramatically as a collision. That word is both useful and misleading. Galaxies are mostly empty space. Individual star-on-star collisions are unlikely. Instead, their gravitational structures will pass through, distort, stir gas clouds, trigger star formation, reshape orbits, and gradually combine into a large emerged galaxy. It will be spectacular on astronomical scales and unhelpfully slow for anyone hoping to watch the finale live. Current estimates place first major interaction in around 4 to 5 billion years, though details remain refined by new data. By then, the Sun itself will be nearing later evolutionary stages. Earth's circumstances may be profoundly changed long before any galactic skyline becomes dramatic. Still, it is striking to know that our neighbourhood is dynamic. The local group is not static real estate. It is a long unfolding story. How do astronomers know galaxies belong to the local group? They measure distances, radial velocities, proper motions where possible, gravitational relationships, and three-dimensional distributions. Nearby galaxies can be studied in detail using standard candles such as Henrietta Swan-Leavitt's Cepheid variable method, red giant branch stars, and other distance indicators. Cosmic neighbourhoods are mapped with careful light. The local group also contains enormous empty regions between galaxies. If planets taught us scale within solar systems, galaxies teach it again. 2.5 million light-years between the Milky Way and Andromeda is a great gulf. Even neighbouring galaxies keep respectful distance, yet compared with larger cosmic structures still ahead, the local group is intimate. Galaxies in giant clusters may crowd more closely and number in the hundreds or thousands. For now, we remain in the small-town version of the cosmos. There is something comforting in that. Our galaxy is vast enough to humble us, but it also belongs somewhere manageable in concept, a local association with familiar named neighbours: Milky Way, Andromeda, Triangulum, companions and dwarves, a short list against a long dark background. The local group likely formed from overdense regions in the early universe, where matter gathered under gravity. Over billions of years, galaxies assembled, merged and evolved into the structures we see today. Smaller systems fed larger ones. Gas cooled into stars. Dark matter halos guided growth. The neighbourhood built itself gradually. Some of the stars in the Milky Way today may have originated in smaller galaxies later absorbed. Streams of stars in our halo preserve evidence of past mergers. Even our own galaxy contains immigrant populations. Identity in astronomy is often composite. Now imagine viewing the local group from far away. You would see two dominant spiral galaxies approaching each other over billions of years, a third smaller spiral nearby, numerous dwarfs orbiting around them, all suspended within an invisible shared mass of dark matter. And somewhere inside one spiral arm of one spiral galaxy, a yellow star with a blue planet. No marker would indicate libraries here, oceans here, worries here, lullabies here. Yet they are there. One of the quiet gifts of learning scale is that meaning survives demotion. We are not the only galaxy, not the largest, not central to the local group, not especially conspicuous from afar, and still life matters here. Sometimes people fear that cosmic vastness makes human life insignificant, but scale measures size and distance, not value. A galaxy can be huge and silent. A small world can be tiny and full of love. Different metrics. The local group also reminds us that local is relative. In daily life, local may mean nearby shops, a short walk, or the next neighbourhood over. In astronomy, local can mean millions of light years. So far, our address has grown in manageable steps. A room became a planet became a solar system. The solar system became one star system inside the Milky Way. The Milky Way became one member of the local group, a small gathering of galaxies linked by gravity. Already that is enough scale to make many ordinary worries shrink politely into the corner. But the universe is not finished expanding our map. Tonight, we move outward again to the next historical layer of our cosmic address, the Virgo supercluster. For many years, astronomers described the local group as part of a much larger concentration of galaxies centered broadly around the Virgo cluster, a massive cluster located roughly 50 to 65 million light-years away in the direction of the constellation Virgo. This broader region came to be known as the Virgo supercluster. The term is still useful historically and descriptively, though modern mapping has refined the picture further, which we will visit next. But first, it helps to understand why this concept mattered. It revealed that galaxy groups themselves gather into still larger structures. Galaxies are not sprinkled randomly through space like salt on a table. Gravity shapes them into hierarchies. Stars gather into galaxies. Galaxies gather into groups. Groups gather into clusters and superclusters. The universe builds upward through association. The Virgo cluster is one of the nearest rich galaxy clusters to us. It contains hundreds to perhaps thousands of galaxies depending on classification and faint members included. Giant ellipticals, spirals, dwarfs, interacting systems, gas between galaxies, dark matter and dynamic motions all belong to this crowded region. If the local group is a small town, the Virgo cluster is a city centre. Dense, busy, gravitationally important, and our local group lies in the broader outskirts connected to that region. For decades, this led to the idea that we inhabit the Virgo supercluster, an immense flattened concentration of galaxy groups and clusters extending over roughly 100 million light-years or more. That is a respectable neighbourhood by any standard. Let us pause and appreciate what changed here. The local group once felt large. Now it becomes one small suburb in a far larger arrangement. The Milky Way, Andromeda, Triangulum and their companions are no longer the main cast. They are one local association among many. Perspective in astronomy often works this way. You become comfortable with one scale just in time to be gently outgrown by the next. What exactly is a supercluster? Historically, the term referred to a large region where many galaxy clusters and groups appeared more densely concentrated than average. Unlike tightly bound star clusters or many galaxy clusters, superclusters are often not single, rigidly bound objects in every part. They are large-scale patterns of enhanced matter density, shaped by gravity but also influenced by cosmic expansion. Some portions may collapse inward over time, other portions may drift apart. Boundaries can be fuzzy. This is common at grand scales. Nature prefers gradients to fences. The Virgo supercluster included not just the Virgo cluster, but many smaller galaxy groups and filaments connected across space, with our local group occupying an outer region rather than the core. So when older astronomical descriptions said, "We're in the Virgo supercluster," they meant our galaxy group belongs to that broader large-scale environment. Still true in a practical lineage sense, even if newer models sharpen the definition. Now let us visit the Virgo cluster itself more closely. At its centre lies a giant elliptical galaxy called Messier 87, often shortened to M87. This galaxy is famous for hosting a supermassive black hole whose shadow was imaged by the Event Horizon Telescope in 2019. That historic image came from a black hole in a neighbouring cluster city. M87 is immense, containing trillions of stars and extending far beyond ordinary spirals in halo size. It helps anchor the cluster's gravitational centre. Clusters like Virgo also contain hot intra-cluster gas, detectable in X-rays. This gas can reach millions of degrees and fill space between galaxies. Once again, The empty regions between obvious objects turn out to be physically busy. The universe keeps doing that because it enjoys consistency. Galaxy clusters are dynamic places. Galaxies move rapidly through them. Some interact gravitationally, lose gas, merge, distort, or change star formation activity due to environmental effects. Compared with our quieter local group, a rich cluster can be a rougher neighbourhood. Our relative distance from the Virgo cluster may have been fortunate for long-term calm. We are close enough to belong to the broader region, far enough to avoid the traffic. Now imagine looking outward from the local group toward Virgo. You would see the Milky Way and Andromeda approaching each other over billions of years, while far beyond them lies a richer concentration of galaxies marking a denser region of cosmic geography. It's a little like standing in a rural town and seeing a bright metropolitan skyline on the horizon, except the skyline is tens of millions of light years away and takes no responsibility for commuting. How did astronomers identify these structures? By measuring galaxy positions, distances, motions, redshifts, and distributions across the sky. Surveys revealed that galaxies form patterns rather than randomness. Regions like Virgo stood out as concentrations. Once enough data arrived, the large-scale map began to emerge. This was one of the great intellectual shifts of 20th century astronomy. The universe was not merely stars and isolated nebulae. It had architecture on scales beyond galaxies themselves. Humanity kept discovering that the map had another page. There is also a psychological effect to these scales. At first, hearing that we are not central can feel diminishing. Not centre of Earth, not centre of solar system, not centre of galaxy, not centre of local group, not centre of supercluster. But another reading is possible. We belong repeatedly. Each wider scale does not erase the smaller one. It includes it. You remain in your room and on Earth, and in the Milky Way, and in the local group, and in the broader Virgo regions simultaneously. Identity layers rather than vanishes. That is true in astronomy and often elsewhere. Now, there is an important update. Modern studies of galaxy flows and mass distributions suggest that the Virgo supercluster concept, while still historically useful, is nested within an even larger and better defined structure called Laniakea supercluster. This newer framework uses the motions of galaxies to trace basins of gravitational attraction, rather than relying only on visible concentrations. In that picture, Virgo remains important, but it is part of something grander. We will go there next. Still, the Virgo supercluster deserves its place in our story, because it was a major step in learning cosmic scale. It taught us that galaxy groups like ours are components of much larger structures. It widened the imagination. Sometimes older models are not mistakes. They are stepping stones. The local group still matters. Virgo still matters. The map simply became richer. Tonight, while you rest on one small planet, the Milky Way belongs to a galaxy group situated in the outskirts of a larger concentration, historically known as the Virgo supercluster. No sensation in your room announces this. The pillow does not whisper, supercluster. The walls remain professionally silent, yet the truth remains overhead. Your address extends through layers of space so vast that language struggles, and still you're simply here, breathing, listening, existing at one precise point within it all. For a long time, the Virgo supercluster was a satisfying answer. It gave structure to our place in the cosmos. The local group belonged to something larger. The Milky Way had a regional context. The map extended beyond galaxies into vast associations. For many years, that felt like a sensible cosmic neighbourhood. Then the map improved. This happens often in science. A useful picture remains useful, but better data reveals deeper patterns. Boundaries sharpen. Motions matter more than appearances. What once looked like one region becomes part of something grander and more meaningful. Tonight we arrive at one of the most elegant upgrades in modern cosmology, Laniakea supercluster. The name comes from Hawaiian and is often translated as immeasurable heaven, or vast heaven. It is a fitting title, though one suspects nearly every cosmic structure could make a similar claim without embarrassment. Laniakea is the larger scale structure within which the local group, the Milky Way and the Virgo region are all embedded. In other words, Virgo was not the whole regional map. It was one district within a larger continent. That metaphor helps. If galaxy clusters are cities and groups are towns, then Laniakea is something like a continent of matter, a broad gravitational landscape containing many clusters, filaments, and flowing galaxy motions across hundreds of millions of light years. We do not merely live near Virgo, we live in Laniakea. How large is it? Estimates commonly place Laniakea at roughly 500 million light years across, containing on the order of 100,000 galaxies or more depending on definitions and included members. Pause there for a moment. Hundreds of millions of light years, perhaps 100,000 galaxies, and our local group is one small node within it. That is the sort of sentence astronomy uses when it wishes to gently rearrange your sense of scale. Now, what makes Laniakea different from the older idea of the Virgo supercluster? The key is motion. Rather than defining structure only by where galaxies appear concentrated, astronomers examined how galaxies move through space under gravity. Galaxies are not just sitting in positions like pins on a map. They flow, drift, and fall through the large-scale gravitational landscape created by visible matter and dark matter. By tracing these motions, scientists identified basins of attraction, regions where galaxy flows tend toward common centers. Laniakea is one such flow-defined region. That means it is less like a painted shape on the sky and more like a watershed on land. Imagine rain falling on mountains and flowing into river basins. Different drops end in different oceans depending on which side of a ridge they fall. Similarly, galaxies move through gravitational valleys and ridges on cosmic scales. This is a beautiful way to think about structure. The universe has rivers of galaxies. Our local group sits within one vast basin whose motions connect it to the broader Laniakea region. The Virgo cluster remains important within this framework, but it is not the whole story. It is one significant concentration inside the larger gravitational landscape. So Virgo did not disappear. It gained context. That happens to us too from time to time. The work formally presenting Laniakea was published in 2014 by researchers, including Brent Tully and collaborators. Using galaxy velocity data, they reconstructed local flows and showed how familiar nearby structures fit into a larger connected system. Maps improved because motion was measured. There is a lesson there. Sometimes to know where something is, you must watch where it is going. Now let's imagine Laniakea visually. Not a solid block, not a bright cloud. Instead, think of filaments and clusters threaded across space, with galaxies tracing lines and nodes like towns connected by roads across a continent. Between those filaments lie vast underdense voids, where relatively few galaxies reside. Matter gathers in strands. Emptiness opens between them. The large-scale universe resembles a web, and Laniakea is one major region within that web. We will talk more about the cosmic web soon, but Laniakea is an excellent doorway into it. Where exactly are we within Laniakea? The local group lies toward one of its outer portions rather than any dramatic centre. Our galaxies move within the larger flow field toward denser regions influenced by structures such as the Virgo cluster and beyond. Again, not central. Again, entirely fine. Central places are often crowded. Our cosmic suburb continues its tradition. There is something emotionally helpful in these repeated decentralizations. Many people hear not central as not important, but nature does not use those words interchangeably. A forest edge can teem with life. A quiet town can matter deeply. A small room can hold tenderness greater than empires. Likewise, one minor galaxy group on the outskirts of a supercluster can host oceans, consciousness, music, mathematics, grief, kindness, tea, and someone listening quietly in the dark. Position is not value. Laniakea also reminds us that even giant structures have limits. Beyond its gravitational basin are other basins, other superclusters, other flow regions, separated by boundaries where galaxy motions diverge. Cosmic geography continues outward. No map page is final for long. And yet, unlike local streets or national borders, these boundaries are not fences. They are statistical, dynamical, shaped by gravity and expansion. Nature prefers soft edges. This is why cosmic structures can be difficult to describe cleanly. Human language likes boxes. The universe likes gradients. Now consider time. Light crossing 500 million light years means seeing portions of this region as they were hundreds of millions of years ago. Some of the distant galaxies associated with Laniakea are observed in eras when Earth's continents, climates and life forms were very different. To map large structure is to combine many different moments into one present understanding. The cosmos does not hand us a simultaneous snapshot. We build one patiently from delayed signals. Another subtle point: superclusters like Laniakea are not necessarily permanently bound into future compact objects. Cosmic expansion driven by dark energy influences the larger scales. Some structures may not collapse into tighter systems, but instead become increasingly isolated over immense time. Gravity gathers, expansion separates, the universe balances tendencies. For our purposes tonight, what matters most is simpler. The Milky Way belongs somewhere larger than itself. The local group belongs somewhere larger than itself, and that somewhere has shape and flow. You may have noticed a pattern through this entire journey. Every time we ask, "Where are we?" the answer becomes nested. In a room, on Earth, in the solar system, in the Milky Way, in the local group, in Laniakea. Each layer contains the previous one. Nothing was lost by going bigger. That is comforting. Wider contexts need not erase intimate realities. Your pillow remains real. Your breathing remains real. Tomorrow's responsibilities remain regrettably real. They simply exist inside a larger frame. Perspective adds space around things. Now imagine viewing our cosmic continent from afar. Countless galaxies stream along filaments toward denser hubs. Voids yawn between structures. One small spiral galaxy among many carries a modest yellow star. Around that star circles a blue world. No sign marks it. No giant arrow says, "Listener here," yet here you are. That hiddenness can feel peaceful. We are not under scrutiny from the architecture of the universe. We are simply included within it. Included is enough. By now, the universe has grown around us layer by layer. A room became a world became a solar system. The solar system became one address in the Milky Way. The Milky Way became one member of the local group. The local group became part of Laniakea supercluster. At each stage, structure emerged where emptiness was once assumed. Tonight, we widen the map again to one of the grandest patterns science has discovered: the cosmic web. This is the large-scale arrangement of matter across the observable universe. Galaxies are not distributed randomly in all directions like glitter shaken into a box. Instead, over immense scales they gather into filaments, sheets, clusters, and nodes, with enormous voids between them. The result resembles a web, foam, sponge, network, or branching scaffold depending on the map and the mood of the describer. No metaphor is perfect. All of them are trying to say the same thing. The universe has architecture. If you could zoom far enough outward, individual galaxies would become tiny points. Galaxy groups would merge visually into denser beads. Superclusters would blend into elongated strands. Between those strands would lie vast regions with relatively few galaxies. Matter gathers in threads. Space opens in between. That is the cosmic web. How large are these structures? Filaments can stretch hundreds of millions of light years. Voids can span tens to hundreds of millions of light years across. Clusters at nodes may contain hundreds or thousands of galaxies. These are scales so large that the Milky Way, once enormous to us, becomes one microscopic citizen in a continental traffic system. Humility arrives again, right on schedule. Now let's ask how such a pattern formed. After the early universe expanded and cooled, matter was not perfectly smooth. Tiny fluctuations in density existed. Some regions held slightly more matter than others. Gravity then amplified those differences over billions of years. Denser regions pulled in more material. More material increased gravity. Gravity drew in still more material. Slowly, patiently, structure grew. Dark matter appears central to this story, because it interacts strongly through gravity and weakly, or not at all with light. It could begin clumping early, forming gravitational scaffolds into which ordinary matter later flowed. Gas collected in these potential wells. Stars formed, galaxies assembled, clusters emerged, filaments connected them. The visible universe likely formed upon an invisible framework. It is difficult not to admire the efficiency. Computer simulations of cosmic evolution are especially striking here. Start with early density fluctuations consistent with observations of the cosmic microwave background. Let gravity operate over billions of years. Web-like structures naturally emerge. The maps and the mathematics begin to agree. That is one of science's quieter pleasures. How do astronomers observe the cosmic web? Partly by surveying galaxy positions across enormous volumes of space. Catalogue enough galaxies and patterns appear. Redshift measurements reveal distance, allowing three-dimensional maps rather than flat sky charts. Projects like the Sloan Digital Sky Survey and many successors transformed our understanding by measuring millions of galaxies. What once looked like scattered dots became roads and walls. Some famous structures identified in these maps include the Sloan Great Wall, immense filaments and sheet-like concentrations spanning over 1 billion light-years in length. There are other giant structures as well, though defining them precisely can be scientifically delicate. Nature enjoys large patterns that challenge tidy categories. Then there are the voids. Voids are not absolute nothingness. They still contain dark matter, thin gas, occasional galaxies, and radiation. But compared with surrounding filaments, they are sparse. Imagine standing in a city centre, then driving far into countryside, then farther into open plain. Voids are the large-scale equivalent of low-density cosmic countryside. Some galaxies inside voids evolve differently because their environments are quieter, with fewer interactions and less crowding. Even galaxies can move somewhere for peace and quiet. At the nodes of the web lie galaxy clusters and rich intersections where many filaments meet. These are busy gravitational crossroads, gas heats to X-ray temperatures. Galaxies interact. Dark matter concentrations deepen. Matter traffic converges. Clusters are the downtowns of the web. Our local group is comparatively modest, but it belongs through nested scales to larger strands within this network. So where are we? Inside the cosmic web, located on one filamentary branch among many, embedded in Laniakea, within the local group, in the Milky Way, around the Sun, on Earth. Still here. The answer keeps growing without losing the centre of your experience. Now let us talk about perspective. The cosmic web can sound cold or impersonal because it is so vast, but there is another way to receive it. It means the universe is not meaningless scatter. It has pattern. It evolved. It organised itself through lawful processes from simpler beginnings into richer structures. Randomness exists certainly, but so does order. That can be comforting. The same gravity that shapes galaxies is the same gravity that keeps your feet on Earth, guides the moon's tides, and holds planets in orbit. The force governing cluster motions also keeps tea in cups when cups are not tipped irresponsibly. Scale changes. Principles continue. There is also beauty in the web's hiddenness. You cannot look up and directly see the cosmic web with your eyes. The night sky shows stars, planets, and perhaps the Milky Way band. The deeper pattern required telescopes, redshift surveys, detectors, statistics, and generations of work. Some truths need patience before they become visible. The cosmic web is one of them. And because light takes time to travel, every map of distant filaments is also a map through time. Farther structures are seen younger. Nearby structures are seen older. A single survey combines different epochs of cosmic history into one reconstructed geometry. We do not receive the universe all at once. We assemble it from delayed messages. Now imagine floating impossibly far beyond our region of space, looking back on hundreds of millions of light years. Threads of galaxies glow faintly. Nodes sparkle where clusters crowd together. Dark expanses separate them. Somewhere in one modest branch, one ordinary spiral galaxy turns quietly. No visible sign says oceans here. No beacon says consciousness here. No highlighted label says your room here. Yet all those things are present. Meaning does not require visibility from afar. This is an important correction to a common fear. Some people hear cosmic scale and feel erased. But being small in a large pattern is not the same as being irrelevant. A neuron is tiny within a brain. A note is brief within a symphony. A person is small within a city. Size alone is a poor judge of significance. The cosmic web measures distribution, not worth. The universe is not an empty box sprinkled with islands. It is a vast evolving network grown from ancient fluctuations threaded with galaxies, clusters and voids. We belong to one strand of that network. There is another humbling point. The web itself is not final. It is the largest clear structure we currently map within the observable universe, but beyond what we can see may lie more patterns, more regions, perhaps endless continuation, perhaps shapes we cannot yet infer. Our horizon limits certainty. That takes us naturally to the next question. What is the observable universe exactly? How much can we truly see, and why is there a boundary at all? By now we have travelled a long way without moving. We began in a room, then widened outward through Earth, the Moon, the Solar System, the Milky Way, the local group, Laniakea supercluster, and the cosmic web. Each step enlarged the map. Each answer to "where are we?" turned into a doorway to something bigger. Tonight we arrive at one of the most important boundaries in modern cosmology, the observable universe. That phrase sounds as though it refers to everything that exists. It does not. It refers to everything we can, in principle, observe from our location given the age of the universe and the finite speed of light. That distinction matters deeply. The observable universe is not the whole universe necessarily. It is the portion whose light or other signals have had enough time to reach us since cosmic beginnings. We live inside a horizon of information. Let us unfold that gently. Light travels fast, about 300,000 kilometers per second. Fast enough to circle Earth many times in 1 second. Fast enough to cross from the Sun to Earth in about 8 minutes. Fast enough to feel instant in daily life. Yet even light needs time, and the universe has a finite age, about 13.8 billion years based on current best measurements. That means there has only been so much time for light from distant regions to arrive. If a source were too far away, and its signals had not yet had time to reach us, then it lies beyond our observable horizon. Not necessarily beyond existence, beyond observation. This is one of the most subtle and powerful ideas in science. Reality may extend farther than what can currently be seen. Now here comes the part that surprises many people. If the universe is 13.8 billion years old, one might expect the observable universe to have a radius of 13.8 billion light-years. But the actual radius is much larger, about 46 billion light-years, giving a diameter around 93 billion light-years. Why? Because space itself has expanded while light was travelling. The galaxies whose ancient light we now receive were closer when that light began its journey. Since then, cosmic expansion stretched distances dramatically. So the observable universe is not a simple frozen sphere measured by age alone. It is a growing horizon in an expanding cosmos. Science occasionally hands us facts that require sitting down, even if we were already lying down. What fills this observable universe? Galaxies. Enormous numbers of them. Estimates vary depending on methods and what counts at faint limits, but there may be hundreds of billions to perhaps trillions of galaxies in the observable universe. Each galaxy may contain millions, billions, or trillions of stars. Many stars likely host planets. The number of worlds becomes difficult even to phrase responsibly. And yet, all of that is still only the observable part. Now imagine a sphere centered on Earth, not because Earth is special, but because every observer naturally sees themselves at the center of their own observable horizon. If intelligent beings exist in a distant galaxy, their observable universe would also be centered around them. This is not cosmic favoritism. It is geometry plus finite signal speed. Everyone gets their own horizon. That is unexpectedly democratic. How do we see the early universe? Because looking far away means looking back in time. Light from distant galaxies began traveling billions of years ago. The farther we look, the younger the universe appears. Eventually we reach the cosmic microwave background, faint radiation released when the universe became transparent about 380,000 years after the Big Bang. Before that epoch, the universe was a hot plasma where light scattered constantly. It was opaque in the ordinary electromagnetic sense. So the cosmic microwave background is like the oldest baby photograph of the observable universe available in light. It has been mapped in exquisite detail by missions such as Planck and WMAP. Tiny temperature fluctuations in that background reveal seeds of later structure, the slight density differences that eventually grew into galaxies in the cosmic web. From subtle ripples came everything large. There is something profoundly calming about that. Great structures can begin as tiny variations patiently amplified. Now let's talk about horizons emotionally rather than mathematically. Humans often dislike limits. We prefer total maps, complete answers, final certainty. The observable universe tells us something gentler. There are limits built not from failure, but from circumstance. We cannot see beyond certain distances yet because information has not arrived. This is not ignorance in the embarrassing sense. It is participation in a finite age universe. Even the best telescope cannot collect photons that have not reached us. Some questions must wait. Others may never be answerable directly, and science is mature enough to admit that. What lies near the edge of the observable universe does not appear as mature galaxies like nearby ones. We see younger systems, earlier epochs, galaxies forming, merging, growing. Telescopes such as James Webb's Space Telescope have pushed observations deeper into early cosmic time, revealing surprisingly developed galaxies in young eras and raising new questions. The frontier keeps moving. Every better instrument redraws the practical horizon, even if the fundamental observable limit remains. There is also expansion happening now. Distant galaxies are generally receding from us because space itself expands on large scales. The farther they are, the faster this recession tends to be, described by Hubble-Lemaitre expansion. Galaxies are not all flying away through pre-existing empty space like startled birds. Space between large-scale structures is stretching. Language strains here, but the physics remains powerful. Because of accelerated expansion linked to dark energy, some distant regions may eventually become forever unreachable in practice. Their future light emitted now may never arrive if expansion outruns the opportunity for connection. Cosmic horizons can harden over time. This gives the present era a special quality. We live at a time when much of cosmic history remains visible. Now let us return to you. You are not physically at the center of the observable universe in any privileged sense. Yet from your location, the horizon surrounds you. If you moved elsewhere in the cosmos, the horizon would shift accordingly. Your room tonight is the center of your observable sphere. Again, not because of status, because every viewpoint begins locally. That idea can be strangely comforting. We do not need to occupy a universal throne to have a valid perspective. We simply need to exist somewhere and look outward honestly. Now imagine standing outside on a perfectly dark night, seeing stars, perhaps the Milky Way, perhaps a distant smudge like Andromeda Galaxy. Hidden beyond naked eye sight are countless farther galaxies. Beyond them, more. Beyond them, early epochs. Beyond them, the microwave background. Beyond that, regions whose light has not reached us. Depth stacked upon depth. The sky is not a ceiling. It is a timeline. And inside that timeline, your life occurs now. Some people hear the scale of the observable universe and feel small. But there is another response available. The universe became old enough, structured enough, chemically rich enough, and locally calm enough for one species on one planet to understand what an observable universe even is. That is not trivial. Matter learned to measure horizons. Atoms became awake enough to ask what lies beyond them. The observable universe gives us a boundary, but not a wall. That is one of the most important distinctions in cosmology. When we say there is a limit to what we can observe, we do not mean reality ends there like the edge of a stage set. We mean there is a horizon beyond which light and information have not had time to reach us, or may never reach us under current cosmic expansion. So naturally, quietly, inevitably, another question appears. What lies beyond what we can see? Tonight, we move into one of the most honest regions of science, the place where evidence thins, possibilities widen, and certainty becomes careful. We begin with what is well supported. The observable universe exists because the universe has a finite age and light travels at finite speed. If space extends beyond our horizon, then regions outside our current view are entirely plausible, even expected in many models. Imagine standing in fog on a vast plain. You can see only to the foggy limit. That does not imply the plane ends there. It means visibility does. The cosmic horizon works somewhat like that, though with more mathematics and fewer damp shoes. In many mainstream cosmological models, the universe beyond the observable region may continue much farther than what we can detect, perhaps enormously farther, perhaps effectively infinite in spatial extent. We do not know for certain. But beyond our horizon is not speculative poetry. It follows naturally from geometry and finite signal travel. Now, if the universe extends farther, what might be there? Most conservatively, more of the same broad ingredients. More galaxies, more clusters, more voids, more cosmic web, more regions with stars, planets, gas, dark matter, and evolving histories. From this perspective, our observable patch could be one neighbourhood among countless others in a larger continuous cosmos. No dramatic border required. No cosmic fence reading end of known area. Just farther regions whose light has not arrived. There is elegance in that simplicity. Now let us consider shape. Measurements of the observable universe suggest space is very close to flat on large scales. In cosmology, flat does not mean two-dimensional like paper. It refers to geometric curvature being near zero overall. If space is exactly flat and extends indefinitely, then the universe may be spatially infinite. If it is slightly curved and closed, it could be finite yet unbounded. Analogous in concept to the surface of a sphere but in higher dimensional geometry. If slightly open, it may still be infinite. Current data constrain possibilities strongly, but do not settle every philosophical desire for finality. The universe remains politely resistant to easy endings. Now we step into more speculative but serious territory. Inflation. Many cosmologists support some version of cosmic inflation, a proposed brief period of extremely rapid expansion in the early universe. Inflation helps explain several observed features such as large-scale uniformity and flatness. If inflation occurred, it may have stretched a tiny region into something vastly larger than our observable patch. Our visible universe could be a small window into a much larger inflated hole, like seeing one tile and asking about the building. Some inflationary models even suggest eternal inflation, where inflation ends in some regions but continues in others, producing many bubble-like universes with differing properties. This is one route to multiverse ideas. Important note: some multiverse concepts emerge from real mathematical frameworks, but direct evidence remains lacking. They are active areas of debate, not settled facts. Science distinguishes between plausible theory and confirmed observation, even when headlines do not. So beyond what we can see may lie more ordinary universe, a vastly larger continuation, regions with different large-scale histories, perhaps domains with different effective physical constants in some speculative models, or something else not yet imagined responsibly. Honesty requires options, not overconfidence. Now let us return to what we know most securely. We cannot currently observe beyond the cosmic microwave background using ordinary light, because earlier epochs were opaque plasma. Yet other messengers may one day deepen access to early conditions, gravitational waves, neutrino backgrounds, improved cosmological probes. Sometimes seeing farther means using something other than light. Human knowledge often advances by changing senses. There is another meaning to beyond what we can see, much closer to home. Even within the observable universe, much is unseen directly. Dark matter, inferred through gravity. Dark energy, inferred through cosmic expansion behavior. Black holes, often known by effects rather than visibility. Cold gas clouds, faint dwarf galaxies, worlds around distant stars, processes hidden behind dust. So the unseen is not only beyond the horizon, it is woven throughout the visible cosmos. Reality exceeds immediate perception at every scale. That can be humbling, but also reassuring. Mystery is not a sign that science failed. It is often the reason science continues. Now imagine beings in a galaxy billions of light years away. Their observable universe would also be centered on them. They might see regions we cannot and fail to see some regions we can. Different vantage points reveal overlapping but not identical cosmic maps. No observer sees all at once. Knowledge is local first, global second. That principle may apply beyond astronomy. What about repeated patterns? If space is infinite or sufficiently vast, then with finite combinations of physical states in regions of certain size, some philosophers and physicists have noted that patterns might eventually recur. There could be distant regions resembling ours in broad ways. This idea is mathematically provocative but highly abstract. It should be handled carefully, not as bedtime certainty that another you is currently making better choices in a parallel kitchen. Still, large numbers invite strange consequences. Another possibility is that some questions remain permanently inaccessible. If no signal can ever cross certain horizons because expansion outpaces communication, then parts of reality may exist forever beyond empirical reach from our location. This can feel frustrating until reframed. Every map in history had edges. Every generation lived beside unknowns. The presence of horizon does not diminish the explored land. In fact, horizons create wonder. Now, let us bring the scale back inward. Your daily life also contains horizons. You do not know every future event, every thought of others, every hidden process shaping tomorrow. Yet life remains meaningful within partial knowledge. The cosmos seems similar. We inhabit a knowable region bordered by mystery. That is not failure. That is condition. And within that condition, extraordinary progress has already happened. A species on one planet inferred cosmic expansion, measured ancient background radiation, mapped galaxy webs, estimated ages, discovered exoplanets, and asked disciplined questions about unseen realms. Matter became curious enough to notice limits. That is a remarkable development. Some people seek certainty the way others seek warm blankets, understandably, earnestly, and often at night. But science offers something gentler than certainty here. It offers reliable humility. We know much. We know more than before. We do not know all. We may never know all. and still, understanding grows. Now imagine the night sky above you, stars nearby, the Milky Way perhaps hidden by city lights or bright across dark country air. Beyond naked eye sight, galaxies. Beyond them, ancient epochs. Beyond them, current horizons. Beyond them, more reality likely continuing whether seen or not. The sky is deeper than visibility. It would be comforting in a practical sort of way if the universe worked like a mailing label. Street, city, country, permanent location. One fixed place where everything could be neatly written down, stamped once and trusted forever. Many parts of daily life reward that kind of stability. Keys belong in one bowl, bills belong in one folder, socks belong with their partners, though this principle is observed unevenly. But the cosmos does not use static addresses. Tonight, we arrive at a truth hidden inside every previous answer. Nothing stays still. Every location we have named, your room, Earth, the solar system, the Milky Way, the local group, Laniakea supercluster, is in motion. Not chaotic motion, but layered, lawful, continuous movement. Your cosmic address is real. It is also moving. Let us begin close to home. Even now, Earth is rotating. At the equator, the surface moves at roughly 1,670 km per hour due to spin. At higher latitudes, the speed is lower, but the turning continues everywhere. This rotation gives us day and night, sunrise and sunset, shifting shadows, and the recurring feeling that mornings arrive faster than expected. You do not feel the spin because you and the atmosphere mostly share it. Smooth motion is often invisible from within. Meanwhile, Earth orbits the Sun at about 30 km per second, roughly 108,000 km per hour. So while you sit apparently still, the planet carries you around our local star at remarkable speed. No seatbelt required, no onboard announcement, no refund options. The Moon circles Earth. Satellites circle Earth. Spacecraft move through the solar system. Tides rise and fall through gravitational relationships in motion. Stillness, once examined, becomes choreography. Now widen one step. The Sun itself moves through the local stellar neighbourhood. Relative to nearby stars, it travels in a definite direction, carrying the entire solar system with it. We are not parked among neighbouring suns. We are passing through a changing district of the galaxy. Stars that are nearby today were not always nearest, and will not remain so forever. Over long spans, constellations distort because stars move along their own paths. The familiar night sky is temporary furniture. Now widen again. The Sun and nearby stars orbit the centre of the Milky Way at roughly 220 km per second. One galactic orbit takes around 225 to 250 million years. That means since dinosaurs roamed Earth, the solar system has completed only part of one grand circuit. Since humans appeared, barely a fraction. Since written history, a trace. Since you began listening tonight, enough distance to make any household errand seem modest. Now widen further. The Milky Way itself moves relative to neighbouring galaxies. It and the Andromeda Galaxy are approaching each other and are expected to merge billions of years from now. The local group members dance through their shared gravity. Beyond that, galaxy groups move within larger structures and flow fields. Laniakea itself participates in cosmic expansion and local gravitational patterns. Even galaxies are commuters, now widen to the larger scale commonly discussed. Space itself expands on average across large distances. Distant galaxies recede not merely because they fly through pre-existing emptiness, but because the metric of space between large-scale structures changes over time. This is one of the strangest sentences physics asks us to accept. The stage itself stretches. So when we say your address is moving, we mean many things simultaneously. You rotate with Earth. You orbit the Sun. You travel with the Sun through local stars. You orbit the galactic centre with the Milky Way. You move with the local group relative to nearby galaxies. You inhabit an expanding universe, layer upon layer motion, and yet your tea can remain on the table. That contrast is delightful. Why do we not notice most of this? Because motion without sudden acceleration often feels like rest. Passengers in a smooth airplane can sip water calmly. People in trains read books while landscapes move outside. Earth's motions are steady enough that local experience remains stable. We sense changes more than constants. This applies in physics and sometimes in mood. Now let us think emotionally. Many people seek a fixed identity, a permanent place, a final version of self, yet the universe around us offers another model, continuity through motion. Earth remains Earth while rotating and orbiting. The solar system remains itself while crossing the galaxy. The galaxy remains a galaxy while interacting and evolving. Perhaps stability does not always require stillness. Sometimes it means coherence while moving. That can be comforting in seasons of change. A new city, a changed job, a shifting relationship, a different body than years ago, a mind learning new weather. Movement does not automatically mean loss of home. Nature manages identity dynamically. There is also humility here. We often speak as though our perspective is fixed and the world moves around us. In reality, no single frame owns all truth. Coordinates depend on reference frames. Are you still in your chair? Yes. Are you moving around Earth's axis? Also, yes. Are you circling the sun? Yes again. Are you crossing the galaxy? Certainly. Contradictions dissolve when frames are understood. This is one of science's nicest gifts. It teaches that apparently opposing truths may simply belong to different scales. Now imagine writing your full current velocity on an envelope. 2. One human currently rotating eastward, orbiting one G-type star, traversing the Orion spur, circling the Milky Way center, drifting with the local group, located within expanding space-time. Postal services may request simplification, but the statement would not be wrong. Another consequence of motion is impermanence in the sky. Polaris will not always be the North Star. Constellations will reshape. Nearby stars will change. Future skies on Earth will differ from ancient skies and modern ones. Even the heavens have eras. This can sound sad until you notice the alternative would be stagnation. A changing cosmos produces new alignments, new worlds, new histories, new observers. Change is the price of ongoing possibility. There is a practical version too. Because Earth moves, seasons cycle. Because the sun moves, stellar neighborhoods evolve. Because galaxies interact, new stars can form. Because the universe changed, atoms assembled into chemistry, planets, life, and consciousness. Static universes do not write rich stories easily. Motion helps make meaning. Now let us return gently to the room around you. It may appear still tonight. Walls quiet, air settled. Perhaps only the faint sounds of plumbing, wind, distant traffic, or a floorboard remembering old responsibilities. Yet beneath that calm, the floor spins, the building orbits, the city rides a planet, the planet rides a star, the star rides a galaxy, the galaxy rides deeper motion still. Peace and motion are not opposites, they coexist beautifully. Some people fear change because they imagine only disruption, but cosmic motion is mostly graceful persistence. Earth has orbited for billions of years. Galaxies rotate steadily. Patterns endure through movement. Perhaps your own life need not be motionless to be okay. Perhaps in progress can still mean at home. Tonight, somewhere in an ever-moving address, you are here now. That now is real even if nothing around it is fixed forever. After all these layers of place, scale and motion, where are we exactly? Not only in coordinates, but in meaning. After all this widening, we arrive somewhere simple. We began in a room, then we stepped outward to your street, your city, your country, your planet. We followed Earth turning beneath you, circling the sun. We visited the moon, the planets, the wide scale of the solar system, the heliosphere, the Milky Way, the local group, Laniakea supercluster, the cosmic web, the observable universe, and the uncertain regions beyond what we can currently see. We watched everything move. We learned that no address in the cosmos is perfectly fixed. And now, after all of that distance, we return to the question that started the journey. Where are we in the universe? Exactly. The scientific answer is long. You're on Earth, the third planet from the Sun, orbiting one ordinary star in the Orion spur of the Milky Way, within the local group, inside Laniakea supercluster, woven into the cosmic web, located somewhere inside the observable universe. That answer is accurate. It is also incomplete. Because coordinates describe position, not experience. Maps can tell you where a forest lies, but not how it smells after rain. They can mark an ocean, but not the feeling of cold water around your ankles. They can locate a city, but not what it means to be lonely there, or joyful there, or young there, or old there. Likewise, astronomy can place you in space. Only life can place you in meaning. So there is another answer. You are here. Not in the vague sense, in the most exact sense available. Here, in this room or wherever you are listening. Here, in this moment of your life. Here, in a body carrying its own history. Here, in a mind that has survived every earlier day that once seemed impossible. Here, breathing on a small world with air gentle enough to breathe and gravity soft enough to walk under. Here, awake enough to wonder. That last part matters. The universe contains stars hotter than imagination, black holes deeper than metaphor, distances larger than language, and structures spanning hundreds of millions of light years. Yet among all of that, one of the rarest things we know of is awareness, matter that can ask where it is. Hydrogen became stars. Stars forged heavier elements. Those elements formed planets. On at least one planet, chemistry became biology. Biology became memory, sensation, curiosity, music, grief, mathematics, affection, and the ability to look up. The cosmos became able to notice itself, at least in one small place. That place includes you. You do not need to be central to be extraordinary. This is worth saying clearly, because many people quietly fear the opposite. They hear about cosmic scale and conclude that small means meaningless. But size and meaning are different measures. A library is smaller than a mountain. A heartbeat is smaller than a storm. A promise is smaller than a continent. A person is smaller than a galaxy. None of those comparisons reduce the smaller thing. The universe is large. That does not make your life less real. If anything, it sharpens its rarity. There may be countless worlds with life. There may be none nearby. We do not know yet. But until proven otherwise, every laugh, kindness, reconciliation, melody, meal shared, child comforted, grief carried, and friendship repaired that we know of happens on worlds like this one. Meaning blooms locally. There is also comfort in knowing you are not separate from the cosmos you study. Sometimes people imagine themselves as tiny outsiders staring at an indifferent universe. But you're not outside it. You're made of the same processes. The calcium in your bones was forged in stars. The oxygen you breathe was made in stellar furnaces. The iron in your blood came from ancient explosions. The atoms in your skin have travelled through older worlds and older suns. You are not visiting the universe. You are one current expression of it. That can be a gentler identity than feeling isolated. And yes, your problems remain real too. Perspective should never be used to dismiss pain. A difficult week does not vanish, because galaxies exist. Anxiety is not cured by hearing about superclusters. Loss does not shrink simply because stars are large. But perspective can sometimes loosen the grip of smaller fears. The embarrassing message, the delay, the mistake replayed at 2 a.m., the future imagined only in worst-case versions. These belong to a mind trying to protect you, yet they occur inside a larger frame. You're on a stable planet under a lawful sky in a universe old enough for healing, learning, and change to be normal features of reality. Things move. That includes hard seasons. We also learned that nothing stays still. Earth rotates. Earth orbits. The sun moves through the galaxy. The galaxy moves among others. Space itself evolves. So if life feels uncertain, you're not failing some cosmic standard of permanence. Movement is the rule. You're allowed to be in transition. You're allowed not to have every coordinate solved. You're allowed to be becoming. Now let us gather the answer one last time, gently. Where are you exactly? You're in a room, perhaps dim and quiet. You're on Earth, warmed by a nearby star. You're in the Milky Way, among hundreds of billions of stars. You're inside vast cosmic structures beyond ordinary imagination. You're in the present moment, which is brief and real. You're part of a universe that produced consciousness at least once. You are here, and here is enough. If tonight you have felt small, let small mean specific rather than lesser. Let it mean finite, located, precious, temporary in the way sunsets are temporary, valuable in the way singular things often are. If tonight you have felt lost, remember that being unable to see the whole map has never prevented meaningful steps. Sailors crossed oceans with partial charts. Scientists built truths from incomplete data. People build lives the same way. If tonight you have felt alone, remember that every person who ever looked up has stood beneath the same larger mystery. Different centuries, different languages, same sky. You belong to a long company of wonder, and if tonight you simply feel tired, then perhaps the most useful coordinate is this: bed nearby, rest available, universe still functioning without your supervision, a reassuring arrangement. So let your thoughts loosen a little now. Let distances drift outward again. Let galaxies take care of their own trajectories. Let the cosmic web remain impressively complicated without your assistance. You do not need to manage expansion tonight. You only need to rest. Thank you for spending this time here on Science for Sleep. If this journey helped settle your mind, you are always welcome back. There will always be more sky, more questions, more quiet things to understand slowly. For now, wherever you are in the universe, good night.